Good morning, everyone. Welcome to today's public workshop, Fuels and Infrastructure for a Carbon Neutral Economy. My name is Jordan Ramalingam, and I will be moderating the first half of the workshop. This webinar is the next in a series of public workshops focused on achieving statewide carbon neutrality by mid-century. Today's workshop will be comprised of two panels, each moderated, followed by a moderated Q&A session and questions from the public. The morning panel will focus on the transition to low-carbon fuels across all sectors of the economy, and the afternoon panel will dive into considerations for low-carbon infrastructure and the workforce as we transition away from fossil fuels. We have an excellent lineup of panelists across academia, industry, government, and nonprofits who are heavily involved in related research, planning, and implementation. And we at CARB are here today to listen and learn about the latest thinking in these areas, and we're very excited about today's topics. After the panelist presentations and a few questions from the moderator, the panelists will be available to take questions from the audience. In order to view the webinar and to ask questions, you will need to register for the workshop at the link on this slide. To ask a question during the Q&A session, click the Raise Hand button in the GoToWebinar control panel. The organizers will individually unmute attendees with their hands raised so they can ask their question. All attendees are, by default, muted upon arrival. And please remember that any questions asked of the panel will be included in the webinar recording, which we will be posting on the website. Written comments will be received to our public comment docket for 3 weeks following the workshop. The link to the docket is on this slide, and the docket will not be monitored during the workshop. As you may recall, AB 32 and SB 32 established ambitious GHG emissions reductions targets of reaching 1990 levels by 2020 and 40% below 1990 levels by 2030. The 2017 scoping plan laid out a cost-effective and technically feasible path for achieving the 2030 target. These targets are milestones on the path to our ultimate goal of deep decarbonization by mid-century. Executive Order S-305 established a goal of achieving 80% GHG emissions reductions by 2050, but the science tells us we need to do more and do it faster. The blue dotted line shows that if we were to carry forward the rate of reductions to achieve the 2030 target, we could achieve the 80% below 1990 levels GHG reduction goal 10 years ahead of the executive order. The concept of carbon neutrality is relatively simple. To ultimately stabilize the climate, the carbon dioxide and other GHG emissions generated by sources such as vehicles, power plants, industrial processes, and natural and working lands must be less than or equal to the amount of carbon dioxide that is removed from the atmosphere. The IPCC special report released in late 2018 finds that to limit the global temperature increase to 1.5 degrees Celsius, we need to achieve carbon neutrality globally by mid-century to avoid the worst impacts of climate change. We believe it is a priority to mitigate emissions from sources to zero where possible. Importantly, moving away from combustion of fossil fuels will result in public health benefits. And only once all mitigation efforts are exhausted should we look to sequestration options to compensate for any GHG emissions left in the economy. There are several interagency collaborative efforts underway that are focused on carbon neutrality in specific sectors. SB 100 charges the CPUC, CEC, and CARB with planning for 100% of total retail sales of electricity in California to come from eligible renewable energy resources and zero carbon resources by December 31st, 2045. Under AB 74, CalEPA commissioned 2 carbon neutrality studies focused on how to reduce demand for fossil fuels in transportation and how to manage the subsequent decline in supply. Researchers from UC Davis and UC Santa Barbara are conducting the studies. And these efforts reflect a growing consensus that in order to achieve our climate and air quality goals, California must reduce and replace fossil fuel consumption across all sectors. Reducing fossil fuel consumption can be accomplished through demand reductions or by incremental energy efficiency improvements. Replacing fossil fuel consumption can be achieved in several ways. Electrification is one major strategy. Electrification is likely to play a major role in decarbonizing most on-road vehicles, as well as building appliances and some industrial processes. However, some end uses may not be suitable for electrification even in the long term. Some examples are aviation, high heat industrial processes, and more. Some of these energy needs that cannot be electrified can be met using other non-combustion technologies like solar steam. However, where combustion is absolutely needed, we need low-carbon alternatives that can replace fossil fuels. As we will discuss in our first panel today, there are several low-carbon alternative fuel options available today. To understand the scale of the challenge of reducing and replacing fossil fuels, we need to understand how fossil fuels are used today. In this diagram, we have depicted the three main fossil fuels in use in California. 4 sectors of the economy are listed as well at the bottom. Now, as we look at each fuel, arrows will appear depicting the amount of energy from each fuel consumed in each sector. The thickness of the arrows is scaled relative to total fossil fuel consumption in California, using the latest inventory data from 2017 data year. A small quantity of coal or coke is still used in the industrial sector, almost entirely at cement plants. Separately, a small proportion of coal is used to produce coke, a finished product which is sold to entities primarily outside the state. Natural gas is primarily combusted to produce electricity at power plants, provide heat for industrial operations, and for commercial residential space heating and cooking. Roughly 1% of natural gas is used as a transportation fuel. Lastly, gasoline and diesel fuel makes up about half of the total fossil fuel energy consumed in the state in vehicles. As you can see, reducing and replacing fossil fuels is a major challenge. And although much of these energy needs can be met by switching to non-combustion technology, we will still need large quantities of low-carbon alternative fuels. And this is not just a short-term issue. The 2017 scoping plan still estimated heavy fossil fuel consumption in 2030, despite aggressive measures. So our panel discussion today will cover several broad themes, including the following. What alternative low-carbon fuels and technologies are commercially available today or on the horizon? Given the limited supply of these fuels, what is the best distribution as we plan for carbon neutrality? And how do we overcome barriers to widespread use of these fuels? So I will now introduce our 4 panelists for this morning's session. Our first speaker will be Chris Battelle. Chris is an adjunct professor at Simon Fraser University and an associate researcher at the Institute for Sustainable Development and International Relations in Paris. After Chris will be Janice Lin. Janice is the founder and CEO of Stratagen Consulting, as well as the founder and president of the Green Hydrogen Coalition, an organization that focuses on building top-down momentum for green hydrogen projects that leverage multi-sector opportunities to simultaneously scale supply and demand. After Janice will be Sam Wade. Sam is the Director of State Regulatory Affairs with the Coalition for Renewable Natural Gas and previously held a number of key roles at CARB. And lastly, we will have Mary Selecki. Mary is a partner at AJW Consulting, and specializes in clean energy and climate policy, particularly across the Pacific coast. So with that, we will transition into our panelist presentations, beginning with Chris Patel. Chris, the floor is yours.
Excellent. Here we go. Well, thank you very much, everyone. It's a pleasure to be speaking here today. So I am a global heavy industry researcher. I look at the world from the perspective of where trade flows, what have you, decarbonization of options across the world. I'm going to be looking at technology and policy pathways to net zero heavy industries. So not very low, but net zero. Now, as Jordan's already articulated, while much of industry can be electrified with clean electricity, there are big sector-specific challenges. First and foremost is the extract, use, and throw away model for most material use. We tend to dig stuff up, process it into something, manufacture it into something useful, and once it wears out, we throw it away. There is some significant recycling of iron and aluminum. That's it. Otherwise, stuff comes out of the ground, gets used, and then gets thrown away with significant GHG implications. We've pretty well maxed out the thermodynamic efficiency of core technologies in most heavy industries. So blast furnaces, cement furnaces, what have you, there are some efficiency gains available, and specifically at the systemic level, but we're not going to get much farther. We need to transition to different processes to really bring down those emissions. The low, medium, and high process heat, while electricity is very useful for low, up to about 100, 150 C, once you started getting north of that, so 250 to 1,000 C or over, you need some other energy carrier to help provide that heat. And that adds up across light industry. That's about 9.7% of global CO2, of combustion and process CO2. Steel, iron ore deoxidization. When we take iron ore to the ground, it's got, oops, pardon me, my phone keeps beeping at me. When we dig iron ore out of the ground, it's got oxygen wrapped around it. We can't use it like that. We have to strip the oxygen off. We currently use coke from coal. We also have to melt it, and that's about 8.3% of global CO2. Cement. The two of the biggest materials that we use today are cement and steel. Cement is effectively limestone that's had its CO2 stripped off using a heating process, and then it's mixed with other materials to make a highly reactive substance that we then use to glue together sand, aggregates, and gravel and stone, creating the material that surrounds most of us. And that's about 6.4% of global emissions. But when we do the heating of that limestone, CO2 comes off. We currently let that just go to atmosphere. Now, this was an interesting one. When I started doing my research, I came to realize that about 5 out of 7 people in the world are alive today simply because we have synthetic fertilizers that we use to run our agricultural system. So, and most of this fertilizer comes from urea, which comes from ammonia, which is made from hydrogen. Now, currently, that hydrogen is mostly made with natural gas and with coal. We do a steam methane reforming process that brought together with water, which then provides the hydrogen. However, we let the CO2 go up we release the CO2 to atmosphere. Along with the fossil carbon feedstock that forms the structure of most chemicals, that's about 5% of global emissions. This is not non-ferrous metals and alloys. The one last big challenge we have is we have to make sure new materials aren't GHG combustion or process intense. Carbon fiber is great stuff. However, it's very, very energy intense to make, and we have absolutely no idea how to recycle at this point in time. However, so that's the scope of the challenge. New literature has shown in the last 5 years or so that are emerging or near commercial options to decarbonize all industrial sectors. We have the technological capability to take this all down to zero. The first and most effective, as with energy efficiency, is material efficiency and circular economy options. We just use less of the stuff. We use way too much cement and steel when we build infrastructure and buildings. We overbuild with it because it's cheap. It's a very safe way to meet strength and safety requirements. We don't need to use as much. We can use other materials, or we can optimize the amount of steel and cement that's in a bridge or a building. And the IEA has shown that we can bring down our use of steel and cement without compromising safety by about 20 to 40%. Now, however, with any amount of material efficiency or circular economy, we're still going to need new raw material. Then we're faced with the choice of keeping existing processes or changing them. If we keep our existing processes, we can use carbon capture and utilization or storage. And there are many different ways to do this. And this actually is an established oil and gas technology with high concentrations of CO2, and we're on the verge of it being commercial with capturing CO2 from post-combustion flue gases. The other way to do this is alternative heat sources. We can use heat at lower levels. We can use heat pumps to move heat from one place to another using electricity. There's small scale direct solar process heat, which is actually a good option in California. As we get to higher heat levels, though, we start needing to use different technologies. So potentially concentrated solar thermal, potentially small modular nuclear. Once we get up to 1,000 C, however, which is what we need for cement, steel, and some chemical reactions, you're going to need something like bioliquids or gases, hydrogen, or potentially synthetic methane. You can do this all electrically, with direct electrothermal technologies, but the electricity demands are very, very high. It would mean you have to tremendously build out your electricity system. The final option here is to change your existing processes. Now, what's interesting is we've done a lot of our chemical, cement, and steel production the same way for well over a century with modification, with improvements along the time. But there are many other ways to do these things, and there are literally 5 different ways that we know of to make steel. We could do it with biomass, which is not going to be really a starter because we need the biomass for other things. We can do it with we can use it with coal, do it with coal and CCS. There are at least 2 ways to do it directly with electricity. You do it indirectly with hydrogen. So instead of using coke, you use hydrogen to strip the iron ore to strip the oxygen off the iron ore and then melt it. Or you can directly electrolyze the iron ore. Now, any one of these pathways will allow us to produce primary steel, but we have to go through a 5 to 15-year period of commercialization to get to the point where these are available technologies. Now, there are dynamic questions that have to be addressed moving through time, and every region, like California, has to ask them. First, material efficiency and circular economy has a very high potential in the long run, but what happens if it isn't easy, cheap, or fast? And it's not likely to be, because we have to retrain our architects or civil engineers, rewrite our building codes, and allow us to do things like use less steel and cement while maintaining full safety in our buildings and infrastructure. Electrification, again, almost anything can be electrified, but capacity constraints matter. Probably the most efficient way to make steel is with electrolytically, but the hydrogen pathway I mentioned earlier, it's less efficient, but it allows you to make hydrogen from electricity or hydrogen from fossil fuels plus CCS at times convenient to you or cost convenient to you, and then do the reduction and melting at times when it makes sense. Carbon capture, utilization, and storage. What happens if CCS reservoirs or CCUS opportunities in a given region are limited? California has some options with its older oil and gas reservoirs, but that would mean you have to pipe the CO2 from your facilities to those old oil and gas reservoirs with all the infrastructure implications that entails. Alternative heat sources, there are regional limits on biomass, solar. Solar is one big resource that California is sitting on. And what about the long-lived legacy facilities with cement, steel, chemicals, what have you? And despite the fact California doesn't do a lot of direct steel making, it imports a lot of steel. So there are your direct emissions there, but but in the long run, if everybody's got to go net zero, you have to consider the GHG intensity of your imported steel. There is a huge fleet of steel plants, cement plants out there that could potentially last forever with retrofits and repair. What do we do? What do we do with those? Do we at key retrofit points? Do we choose not to replace them with low emissions technologies? Do we choose? Do we put up some sort of barriers, what have you, that allow those new technologies to grow within your jurisdictional bubble? These are questions that are explicitly germane for policy. And can we build situation-specific technology and policy hybrids to solve for all the above? Now, one possibility for heat and feedstocks, are there potentially regionally tailored hybrids of electricity, hydrogen, biomass, and what we call synthetic hydrocarbons? I won't go through this diagram in any detail. The slide deck will be available afterwards. But if you can generate a surplus of decarbonized electricity by whatever means is appropriate for your jurisdiction over and top your direct electrification requirements, you can make hydrogen and oxygen from that, and you can also make the hydrogen from methane with CCS. So this gives you potentially two clean energy carriers to work with, and the hydrogen, it's a gas. It has to be transported gas, but you can compress it into a liquid. You can catalyze it into ammonia, and ammonia can be, if it under light pressure, turns into a liquid and could literally be shipped across the ocean, much like we ship crude oil today. Now, where this gets interesting is now that if we have clean hydrogen and oxygen to work with, if you have an access to what are called net zero carbon sources, potentially from captured carbon, from gasified biomass, or in the long run, direct air capture, you can combine your hydrogen, your oxygen, and your carbon into basically any molecule you want. You can make methane. So there's the question of, what do you do with all your existing legacy gas users? So the real estate, the industry, what have you. You can make synthetic. You can take it from biomass gasification. You can amplify the amount of methane that's made by adding clean hydrogen to the biomass. You can make methanol. You can make ethanol. You can make potentially jet fuel, chemical and plastic precursors. Once you have enough clean electricity and enough clean hydrogen to work with and clean carbon, you can basically recreate much of the economy that we have today. But you need those primary energy sources and feedstocks. So I won't spend too much time on this because I don't want to take too much time from the other panelists, but these are global emissions today, and I'm going to walk through how we might clean most of them up. The direct electrifiables on the bottom are about 43% of global emissions. Our legacy buildings and industry, we can retrofit it to electricity or hydrogen, or we can potentially, for their life, because they're so valuable and generating so much GDP, and we don't want to shut them down for the time it takes to retrofit them, we can use drop-in bio or synthetic gas replacements to keep them going. Another key area that researchers spend a lot of time thinking about is, what about your firm electricity? As your electricity system goes to higher and higher levels of solar photovoltaics, wind, what have you, how do you maintain the stability? How do you maintain the stability of the system? You can add in some flexible fossil and CCS, more transmission to other regions, such as my home province of British Columbia with our hydro dams. You can add potentially some nuclear batteries on the shorter end of the time scale, hydrogen fuel cells. So when clean electricity is plentiful, you make hydrogen, and then you pass the hydrogen back through the fuel cell when you need that electricity. There are losses, but it does keep the system going. Or bio or synthetic gas turbines. Now, coming back to iron and steel, the first thing is material efficiency, and then you can work with hydrogen electric arc furnaces, molten oxide electrolysis, or potentially direct smelting methods that allow you to do concentrated CCS. So there are lots of options there. Cement and lime, again, material efficiency. A key one here is clinker substitution. In North America, we use too much what's called ordinary Portland cement when we make cement. A lot of regions use a lot less, probably 30, they only use, it's 60, 70% OPC. The less clinker that you use when you're making concrete, if you can substitute it with ground limestone, with blast furnace slag, fly ash, or heated clays, those are direct substitutions from the amount of clinker that needs to be made, the emissions that goes with that. And then fertilizer production, you need net zero carbon, hydrogen, heat sources, and then for heavy road freight, aviation, and shipping, you need some mixture of electrification, hydrogen, or drop-in liquid or gas fuel replacements. Now, just a quick, I'm not going to go through this entire list here, but it is available on the slide deck. If to make this vision possible, we need a diversified portfolio or toolbox of technologies that can be commercially bought from companies that are used based on regional resources and needs. And it's a whole sequence of technologies here that I've kind of run through. But if you're interested in them, happy to answer questions about them afterwards or offline after the talk. Now, moving on to the policy, simple carbon pricing and regulations are not going to be enough. The challenges are much more than technological. While the emerging technology exists, innovation will be slow because of low profit margins. These industries are very competitive. They can't pass on costs without losing market share. The capital costs are very focused and upfront. They often can't capture the benefits of innovation. Once a thing is invented, it's very easy to reverse engineer. And it's hard to impose IP controls across borders. Facility lives are long and stock turnover is slow. And there is no market for more expensive low GHG materials. One of the key things here is that in order for companies to take the risks of bringing new low GHG steel, cement, and chemicals to market, they need to know they can sell it at least their cost basis plus a small profit. And one of the key things that jurisdictions like California, Canada, and EU and the British jurisdictions can do is start to provide that preferential green procurement contracts for difference on the excess cost above, what have you, help perform private buyer coalitions. So imagine if Tesla only agreed to buy up all the green steel available at a 40 to 50% premium. It would add almost nothing to the cost of the vehicle, but that market would be there for the steel companies to sell into it. It literally would add about $300 to $400 to the cost of an average Tesla. Policy for heavy industry needs to target these challenges directly. And fundamentally, this is about reducing and controlling risk. Now, this is my last slide here. Combined strategies for a local solution finding policy package. You need a multi-level policy commitment to transition to net zero GHG industry, and California is one of the global leaders in this. In terms of material efficiency, we need building code, design, and recyclability policies that enable material efficiency and circularity, and this has to go with education for architects, civil engineers, and regulators. You need a transition pathways process, including all key stakeholders, to assess your strategic and technological options, your competitive advantages, and your uncertainties moving forward. And you're going to need accelerated R&D and commercialization. Create those lead markets that build the economies of scale. And I already talked about green procurement and supply chain branding, what have you. Eventually, you're going to need full exposure of all sectors to full GHG pricing with competitiveness protection. You can imagine there's probably going to be about a 10 to 15 year period where you're not going to be able to fully put a cost on steel, cement, and chemicals producers. Every region does some exemptions for these because they're so GHG intense. But as you help them develop new technologies, as you reset the best available technology to these very low emissions level, you have to start adding full GHG pricing to the full system. But in order to do that to your domestic firms, you've got to build protection for them in terms of border carbon adjustments, border standards, what have you. And the Europeans are already talking about doing this, and I think California is already doing this for a couple of different commodities. And there's probably going to be early retirement if necessary for long-lived, highly GHG intense facilities. So, and supporting institutions. You're going to need just transition for workers, retraining, monitoring how well are your policies working in terms of reestablishing best available technology. How are your steel, cement, chemicals, and other heavy industry firms doing under? How is their progress coming along with GHG intensity? You're going to need to build out electricity, hydrogen, and CCS infrastructure. Government always has a role in that in terms of establishing it and then helping regulate it afterwards, because it tends to be a natural monopoly. And you're going to need life cycle in order to do GHG pricing over the long haul and border carbon adjustments. You're going to need bulletproof life cycle GHG intensity accounting for materials. And again, the education and regulatory backdrop. So in summary, net zero industry is possible, but it will require planning as well as subtle, staged, and stringent policy. And that's it for me. Thank you very much for giving me your time.
Great, thank you for that presentation, Chris. As a reminder to the audience, we will take questions after all the panelists have presented. And at that time, you can click the raise hand button to signal that you'd like to ask a question. So our next speaker is Janice Lin. Janice, you can go ahead and begin.
Are we good, Jordan?
Yes, we are. Thank you
so much for the opportunity to present here today. I think this presentation was excellent and a great setup for what I wanted to talk about, which is my favorite topic, the opportunities and challenges for green hydrogen. So just a quick intro about what is the GHC. As Jordan mentioned earlier, we're a new nonprofit, and our mission is to facilitate policies and practices to advance the production and use of green hydrogen in all sectors where it will accelerate a carbon-free energy future. Our approach is a little different than other nonprofits focused on hydrogen. One, we're just focused on green hydrogen, which I will define in a moment. And two, because our thesis is that the challenge for green hydrogen is not a technology problem. There are many technologies that are commercially available today. It is one of scale and market design. Our approach is to focus on specific large-scale infrastructure project deployment at scale, where we can creatively think about aggregating demand and driving down cost. So I'm going to talk about today why we believe green hydrogen is a game changer in our fight against climate change, and as well as some of the challenges and opportunities before us. So first of all, to start with, I just wanted to say that many of the topics Chris mentioned is hydrogen is one of those fundamental building blocks in many industrial sectors. This is a tiny molecule, it's extremely abundant, and it is a flexible alternative fuel that can decarbonize sectors we never dreamed possible, including aviation. But first, let me start with some of the core facts just today on how hydrogen is used today. And that is, as a globally traded commodity, hydrogen produces more GHGs if it were treated as a country than Germany. It produces more GHGs than even the global aviation sector. And the reason for this, as Chris mentioned, is hydrogen today is produced primarily from natural gas and coal and some oil, all fossil fuels. And that produces a lot of GHGs, and this is a huge opportunity. And the good news is we don't have to make it from fossil fuels. There are ways we can produce hydrogen from green sources, from zero emission electricity, solar, wind, hydro, for example, through electrolysis, and also from biomass or biomethane, either through SMR, reforming, or thermochemical gasification. All of these pathways are commercially available today. I think they are classified as emerging because they have not scaled in the same way, say, that solar and wind have scaled, but they are commercially available, commercially viable today. So what I wanted to talk about first is the many ways, 5 key reasons why we believe green hydrogen is a super game changer. My hope is at the end of this presentation, you'll be as excited as we are. I will go through each one of these in turn. And by the way, for those of you who may be a little skeptical, because I know there's a lot of people on this call, I'll just share a tiny story. I first heard about green hydrogen about 15 years ago from a Fraunhofer Institute scientist. He visited my office in Berkeley and explained to me how green hydrogen was going to be made with solar and wind, decarbonize the electric sector, the transportation sector, the gas sector. And at that time, this was 15 years ago, I had this meeting, and at the end of the meeting, I'm like, wow, that's a big idea. And my second thought was that was about the kookiest thing I ever heard. Well, here we are 15 years later, and that Fraunhofer scientist, everything that gentleman predicted has come true. And while 15 years ago, I was not ready, today, I think the world has changed. And there's a number of reasons why I no longer think it's a kooky idea. In fact, I think green hydrogen is a super game changer. And I'd like to run through those reasons now. First of all, today, renewables, solar and wind, is now cheaper than fossil generation on the electric side in most countries around the world. You know, a good friend of mine who works for a integrated oil and gas company says, hey, the electrons are cheaper than the molecules. So this is very, very good news. Secondly, according to the International Energy Agency, when you forecast out, again, sticking to electrolysis, which is only one way of making green hydrogen, but when you forecast out the cost, future cost of solar and wind, which are the green and the blue lines here, and you compare the resulting cost of hydrogen on a dollars per kilogram basis to hydrogen made from fossil fuels with carbon sequestration, so that's this gray bar in the middle, within, you know, the next 5 years, hydrogen made from solar and wind will be cost competitive and at parity with hydrogen made from fossil fuels with carbon sequestration at scale. That's within 5 years. And when you project out, it's looking like the green hydrogen's even going to be cheaper and competing with hydrogen, pure gray hydrogen without carbon sequestration. That's very good news. We are on the trajectory to be lowest cost. Another reason, and you will hear more about this project during the second panel, this is one of the GHC's first major infrastructure initiatives, which is to support the conversion of this beautiful coal plant in southern Utah, which is scheduled to be converted from a coal plant on July of 2025 to a combined cycle that will initially combust a blend of natural gas and green hydrogen, taking that percentage up to 100% green hydrogen made from solar and wind on or before 2045. This is a beautiful example of not only repurposing existing infrastructure, the plant itself, available interconnect, available plentiful renewables, but also the repurposing of a really skilled workforce that's been there for many, many years, and transitioning that workforce to doing, continuing to produce wonderful electricity, clean electricity going forward. The other thing, you know, I could put a lot of pictures in here. We could have a picture of a biomass plant, one of many in California that have been retired, that could be repurposed to commercially available gasification technologies that can convert, say, agriculture waste to green hydrogen and very easily sequester the CO2 to be not only carbon neutral, but carbon negative. We'll talk about more about that in a minute. Another key point, hey, those, you know, the existing global commodity, roughly 70 million metric tons of hydrogen produced and sold today around the world, we could decarbonize this. And if you believe the trajectory that the IEA presented, all of these end uses, so this is a chart from IEA that shows the sources, the current today end uses, these could be converted to green hydrogen. Imagine oil refining, assuming we still need oil refining, that uses only green hydrogen. Imagine ammonia. Most of this goes towards making fertilizer produced with green hydrogen. We could have green fertilizer. Right now, transport's a small slice, but as Chris said, you can expand this greatly, not only for direct use, green hydrogen, and say medium and heavy duty trucking, but green hydrogen is a precursor ingredient to making synthetic fuels that can be used for shipping and aviation. The bottom line is this is the picture today, but these bars on the right could be grown substantially, displacing fossil fuels that are used in other sectors. Another application, that green hydrogen today, there are fuel cells that are commercially available today that are primarily optimized for emergency backup. What you see here is a picture of a fuel cell running on pure hydrogen used to provide emergency backup to a traffic signal. These types of systems are deployed everywhere. They're very low maintenance. Why aren't we using these for microgrids and to help us as an alternative to diesel and gas backup generators? So in summary, you have a tiny molecule. Today, it's a gray molecule that's made from fossil fuels. We have commercially before us a way to make this molecule from green, zero carbon sources, and this molecule can go into so many sectors. So the conclusion, it has the potential, or super game changer, to reduce emissions across many, many sectors, even aviation. So we talked about hydrogen creating a synthetic fuel for, say, long-haul aviation, but there is a company, Zero Avia, that is commercializing a short distance, roughly 20 passenger plane that is running on a fuel cell and is going to be powered by green hydrogen in the near future. Okay, and then the last couple reasons why we believe it's a super game changer. For the visionary jurisdictions that have set a goal for themselves to achieve 100% renewable energy, we are going to need low-cost seasonable storage. And this was actually the chart that we developed in 2016, just taking the CAISO OASIS data and amping it up to where such that 100% of generation came from renewables and met demand. And what you see on this chart, this is a year-round chart of a flock of ducks. So each one of these blue lines is a duck curve. And as you can see, in the wintertime and in the autumn, we do have deficits. In the spring and summer, we have surpluses. There's even multi-day deficits in the spring and summer. What are we going to do about this? As you know, there are many different types of storage commercially available today. I was the co-founder of the California Energy Storage Alliance. I love all types of storage solutions. When it comes to seasonal solutions, there really aren't many other choices besides hydrogen that are commercially viable today and can do that type of storage at this scale. So great option for seasonal storage and getting to 100%. So in summary, we believe that green hydrogen is key to carbon-free energy supply across sector. It's going to help us overcome very difficult challenges, getting to very, very high penetration of very low cost renewables. We're going to be able to decarbonize hard to abate sectors, the ones that Chris just reviewed. We can enhance our energy security by diversifying our fuel supply. And we know that the challenges are fundamentally market design related. How do we achieve scale to reduce costs? How do we compensate for all the benefits provided? At the end of the day, securing appropriate compensation for a high capital intensive project is the key to bankability. We also need to think about hydrogen as part of our planning toolkit, as an integral part of our integrated resources planning, both on the electric and gas sector and transportation sector. And these opportunities exist today, but this is going to require a multi-jurisdictional focus. So our recommendations, and here's our recommendations for how to address these challenges, is a new paradigm. I challenge everyone on this call to think about the opportunities for green hydrogen, think beyond sectors, beyond silos, and what is needed. We need system-wide transformation. We need planning across sectors, and we need to value all the benefits, not just the cost. So really what we need is a mind opening. And when we talk about valuing benefits, not just the cost, my favorite example is typewriters versus computers. Nobody buys typewriters anymore. It's a single purpose. We spend thousands of dollars on laptops because they deliver so many benefits. And hydrogen production, just like that laptop computer, may not be the cheapest thing on the block, but it can deliver lots of benefits. Electrolysis can produce green hydrogen. It's also a load modifying resource and can deliver ancillary services to a wholesale market. And of course, we have, as Chris called it, the full GHG benefits. We need to make sure that those GHG benefits are fairly and appropriately valued. Once we get the value proposition right and recognize all those benefits, which will require regulatory innovation, a virtuous cycle will take over, where suddenly the value exceeds cost, it's bankable, we get more projects, larger scale, and the cost of the equipment will go down. Look what happened to PV, look what happened to solar, look what's happening to lithium-ion batteries. And that's how you get continuous progress, impact, and innovation, because once you get the formula, the economic formula right, we will attract lots of capital and infrastructure investment. There are literally trillions of dollars of infrastructure dollars that want to find a home, and it's up to us to create the right market structures that create this virtuous cycle. The good news is this is already happening around the world. One of the key drivers is countries waking up to the fact that hydrogen is a game changer. In fact, on July 8th, the European Union released its hydrogen strategy, very ambitious targets, 6 gigawatts of electrolyzers by 2024, 40 gigawatts by 2030, and 10 million tons of green hydrogen production. And by 2030 to 2050, their goal is to deploy hydrogen at large scale for the really hard to abate sectors. And this is a exhibit that they released last year. So we can do this too. And so I'll just wrap up here by saying, we think that this is entirely possible for the United States. I firmly believe that California will lead the way. And I also believe that ARB, thank you for hosting this workshop and this webinar and all your efforts in leading a cleaner energy future. But we would like to respectfully recommend that ARB lead a multi-jurisdictional task force. It's a couple of activities that need doing. One is to define green hydrogen broadly, and we need to make sure that we're accounting for the emissions benefits of green hydrogen and its eligibility towards SB 100 compliance. Setting decarbonization targets or procurement goals. Goals are really important as a market signal. These can be economy-wide. What if we had targets for decarbonizing the pipeline, for decarbonizing thermal electric generation for the remaining plants that we do need to keep online for reliability purposes? What if we had targets for greening up our agriculture? California is one of the food production baskets of the whole country, yet we import so much fertilizer and ammonia from places like Texas. What if we had not only organic, but green organic that had low carbon branding? What if we had oil refining in California that was made from green hydrogen? So these are just some what ifs. I think ARB is also in a great position, looking over many sectors to coordinate the development of new tariff designs and market incentives. We need a wholesale electric tariff to enable curtailed and purpose-built renewables to make hydrogen with electrolysis. This can be done from anywhere on the grid. Interconnection, we need new interconnection rules, both for CAISO market participation and gas pipeline injection, and we need incentives. For example, currently a lot of ag waste is simply put in an open field and burned. What if we reuse that to make hydrogen? What if we had full GHG pricing, as Chris says, across all sectors? And so this progress will require multi-jurisdictional focus. And I will just leave everyone with this, my favorite quote from Margaret Mead: "Never doubt that a small group of thoughtful, committed citizens can change the world." Indeed, it's the only thing that ever has. Thank you.
Thank you, Janice. Our next presentation will be from Sam Wade. Sam, go ahead and begin when you're ready.
Well, thanks very much for the opportunity to be here today. I really appreciate the chance to follow Chris and Janice as well. Certainly share their vision of what we need to do to further deploy low carbon fuels across all end uses and achieve California's carbon neutrality goals. Just a little bit about us. The Coalition for Renewable Natural Gas is the national trade association for the pipeline interconnected renewable natural gas industry. We represent 98% of the supply in North America currently. So I'm going to focus a little bit more than Janice did on the feedstocks that are related to our organic waste streams, because we strongly believe that a key part of achieving carbon neutrality is going to be effectively using those feedstocks for their energy value. And so we use the umbrella term renewable natural gas as something that's interchangeable and a drop-in substitute or a replacement for conventional natural gas. And the most common commercially available type of renewable natural gas available today is biomethane, which is derived from these organic materials that I'm talking about, including food waste, wastewater, agricultural waste, and landfill gas. So, I think we've already heard from the prior presenters about the importance of using RNG and the value of using that to achieve carbon negative or carbon neutral performance. But I'm going to just quickly touch on that based on a few studies. The first and most interesting one from our perspective is some work done by Lawrence Livermore National Labs specific to California's goals, and it's called Getting to Neutral. And, it encompasses a lot of different technologies, but of course, it refers to pipeline renewable natural gas as a key part of things. The second study I'm going to talk about a little bit is done by UC Irvine and the consulting firm Energy and Environmental Economics. And they look closely at electrification of buildings and also look at how biogas and renewable natural gas can complement that electrification. So we think that's important as well, that there's no sort of need to think about electrification and the use of low carbon alternative fuels as competitors. Really, they're both going to be needed to achieve our long run goals. And that's shown very well by this last study that EFI did, focusing on optionality, flexibility, and innovation to get to these targets. So they all agree that there should be widespread use of RNG, especially the biomethane portion of things. Digging a little bit more into the Lawrence Livermore work, this is a very similar figure to what Jordan showed at the outset. To achieve our long-term goals of carbon neutrality, we need to go beyond what was called for in the last CARB scoping plan and really begin to think hard about negative emissions from these organic wastes, and really getting the natural and working land sector more involved in developing carbon neutral fuels or carbon negative fuels. The Lawrence Livermore report does a great job of outlining how that might work, and it talks a lot about waste biomass conversion to fuels in the long run with CO2 storage. And we think that the current sources of RNG fit very well into that strategy. And in fact, it's one of the few fuels that can be produced today with carbon negative performance. I mean, basically that it avoids more emissions than it produces over its life cycle, or it sequesters a significant amount of CO2 over its life cycle. And digging into that overall life cycle performance a little bit more, luckily, California's low carbon fuel standard program has that, I believe Chris called it the need for bulletproof life cycle accounting. So it has that ability to look across how the fuel is produced, how it is moved to its end use, and how it is used in the case of the LCFS in vehicles. And that framework shows that a lot of the agricultural waste sources of RNG that are commercially available today are in fact carbon negative. And that scoring could easily be adapted to non-vehicle uses by basically removing the steps that are most relevant to vehicles. When we look at that across all of the life cycle scoring that CARB has done in the LCFS, as I said, the ag manure projects have the best performance. They are carbon negative, if you will, on the far left-hand side of this chart. But even the landfill projects and the wastewater projects that are commercially out there today perform much better than conventional gas or diesel, and could be made to perform even better by decreasing methane leakage and the energy used to upgrade the gas, and eventually, as Janice said, by including maybe carbon capture and sequestration and conversion to hydrogen. There's also the need to promote landfill diversion and the use of organic wastes outside of landfills, either through composting or through anaerobic digestion. And that's a goal of CalRecycles that they've recently passed regulation to help fulfill. And those projects will receive better scores on this type of sliding scale than the landfill projects will. So just going into the opportunity of these organic waste feedstocks a little bit more, both for California and nationwide, we'll see that they're basically untapped right now, and we need more policy support to continue to move these feedstocks into productive end uses. So this is a busy chart, apologies for that, but basically what it is a summary of all the recent potential studies that have looked at the California supply of these various organic waste derived feedstocks that can be used to make the biomethane type of RNG. And if you look at the far right-hand side of the figure, you can see that compared to the total demand for gas in 2018 in the state. So, the renewable natural gas supply from these feedstocks could displace somewhere between, we believe the best estimates to use are this 10% to 17% or maybe 19% range. So not going to displace all of conventional gas, but certainly going to make a big impact and could be deployed relatively quickly to displace a large share of conventional gas demand. Digging into that more, this is from the ICF work that was done recently. We can look at the individual feedstocks. As Janice said, some feedstocks are more suitable for anaerobic digestion, and some require thermal gasification. The anaerobic digestion projects are underway today and being supported by policies including support. We're going to deal with the forest issues, including wildfire risk. Forest residue could be a big feedstock, and so we need to think hard about how to properly deploy policies that promote that sort of RNG in a way that deals with issues like methane leakage, et cetera, appropriately. So the other thing I wanted to say overall is that U.S. feedstocks, represent a much larger source of supply, obviously, that California might be able to tap into in the near term until other jurisdictions begin to try and use them as well. So what we're doing really is we're focused on pipeline interconnected projects that can use the existing gas infrastructure, where currently methane is the energy carrier, to displace conventional gas. And we're seeing a great growth in those types of projects due to California's policies and to some extent the renewable fuel standard at the federal level. We're up to 129 operational projects in the U.S. that are pipeline connected. And basically our point here is that the use of pipeline interconnected RNG can be shifted to whatever sector needs it over time. So, I think Chris did a great job outlining some of the most difficult to decarbonize sectors from his perspective today. But if you have, the ability to shift this RNG to whichever sector needs it over, the long term, we think that's a smart strategy. And it may involve eventually turning the RNG into hydrogen, as Janice spoke to, or other, liquid fuels if necessary. So just talking a little bit more about what's out there today, landfill gas is the most established form of RNG, and there's over 564 operational biogas and RNG landfill projects. As you can see on the right-hand side, most of those are going toward electricity rather than pipeline interconnection right now. And we feel like, that may or may not be the right long-term use of it. As I said, you don't have too much optionality if you have a small, method of producing electricity on site as your primary use of this gas. And so we're more interested in taking it to the pipeline and then leaving it to the policymakers to decide how it should be used over time. But there's still a lot of potential here. There's still, over 481 candidate landfills, as well as some of these shutdown projects that could be done to better utilize the existing landfill resource. And then there's also a huge amount of growth potential in agricultural projects. US EPA's AgStar estimates that there could be over 8,000 farms where these types of projects could be done. There's only 255 operational projects right now. So diving into the costs a little bit, these are sort of cost curves on a dollar per MMBTU basis. The one on the left is for California or California's population weighted share of the US total supply. And the one on the right is a nationwide look. They both sort of agree that biomethane is lower cost relative to other types of renewable gas like hydrogen and synthetic methane. But that could change over time, as Janice shared, the electrolytic costs coming way down, which is exciting. But right now, we're pretty sure that the biomethane and the use of these organic waste is the low-cost resource, and that the technology is very ready to go, as Janice also pointed out. So we believe we have to get started on at least the biomethane portion of the supply curve in a more aggressive way, and that you need to think about that in transition to other resources or other energy carriers in the long run, like hydrogen. And that's shown here from this figure from Lawrence Livermore again. They think that in the long run, these uses of these feedstocks, when coupled with carbon capture and sequestration, can produce negative emissions performance, and that the long-term energy carrier should be hydrogen. And we're totally fine with that vision. We think what's the way to sort of incrementally approach that is to begin to build these types of facilities now, produce the methane and displace conventional gas, and then in the long run shift toward doing CCS and hydrogen production once there is a viable system to carry that hydrogen to end markets. There's still a lot of challenges, as I've already alluded to a bit, with deploying RNG at scale, and we need additional policy support. But just to speak to those briefly, projects today are coming online, but they still face significant operational risks based on feedstock availability and the consistency of these materials and equipment failure that relates to learning a new feedstock. The economics are not great unless supported by programs like the Renewable Fuel Standard and the Low Carbon Fuel Standard. And they have both significant, capital costs as well as ongoing operational maintenance costs that you don't see for, other sources of renewable power, for example. There's a large market risks in these policy-driven credit markets right now. There's big swings in credit prices historically. And so, this investing in these spaces is not for the faint of heart. But in the long run, additional stability in those policies and new policies can help provide folks with the strong enough incentives to begin to deploy the type of project. And so just as a case study, we've seen, as I mentioned, the California LCFS being a strong driver for the use of renewable natural gas in the transportation sector. Shown on the left side of this chart is the prices for LCFS going up over time, and the RIN prices at the federal level and the fossil natural gas price sort of fluctuating as well. But because LCFS provides such a strong signal, we've seen on the right-hand side here, the renewable natural gas going into vehicles, almost completely displacing the conventional natural gas in that sector. And so these programs work. Disincentives, are clearly driving the fuel switching that we're trying to see. The only issue is that the end-use sector of transportation, as Jordan mentioned before, is a very small demand for conventional gas. So on the right-hand side of this chart, we sort of show that the vehicle filling stations represent about 1% of 2018 natural gas demand, and these other industrial, residential, and commercial applications represent much more demand, and of course power as well. So in California, we still lack good policy support for use of RNG in these sectors, especially in maybe the industrial applications that Chris mentioned are potentially the hardest to decarbonize with electricity. So to me, that means that our policy support is misaligned. And while the growth in vehicle use is fantastic, we need more long-term, life cycle-based policies that support RNG use in these other end uses. So, in conclusion, we really believe that the RNG is going to be an important part of achieving carbon net neutrality for California and really for the world. And that some RNG already is providing carbon negative performance today. We don't want to get in the way of the long-term vision, both as it relates to efficiency and electrification, and also potentially as it relates to using hydrogen as an energy carrier. But we believe we can have a big impact right now, even if the molecule we're working with is methane. And when you're working with methane, it's important to be very careful in your greenhouse gas accounting and be sure that you are minimizing the life cycle emissions from producing and using the fuel. But there's also an opportunity there because there are big sources of methane that could be captured and used productively. So in the long run, implementation of a renewable gas standard in line with the legislative direction from Senate Bill 1440 of 2018 would be very helpful. And that renewable gas standard should incorporate both biomethane and also hydrogen and synthetic natural gas, ideally. And similar policy support should also be developed by CARB to incent the same type of fuel switching by non-core customers, especially the industrial sector. So that's my my summary here, and certainly appreciate the chance to be here again. Thanks.
Great, thank you, Sam. We're going to move into our last presentation for this panel before we do the Q&A session. And the last presentation will be from Mary Selecki. Mary, the floor is yours.
Hi, everybody. Thanks, Jordan, for the opportunity to be here today. I'm, as Jordan said, Mary Selecki. I'm with AJW. We're a consulting firm, and we represent, among others, a range of different renewable fuel companies. And so I have the opportunity and the privilege of working closely with a lot of different technology providers. And so today, CARB asked me to speak about some of the fuel solutions for hard-to-electrify sectors. And there are many small scenarios where electrification is difficult, but there are several key areas the state should account for and is starting to account for in its planning. And those are listed right here, obviously, being aviation, long-haul trucking, rural, and industrial. Just a couple of background slides. CARB is working to reduce light-duty vehicle emissions to zero, as we all know, as quickly as possible. But electrification does have its limits. As the Clean Air Task Force states in its report, Fuels Without Carbon, electrifying all light-duty vehicles by 2040, which would be a difficult task, would reduce oil demand by 25 million barrels per day. Even if this were achieved, this leaves 35 million barrels per day in demand from trucks, trains, ships, and aircrafts, and that's using IEA data. Now, the Advanced Clean Truck Rule that CARB board just voted on will definitely help with the freight sector, but this sector still won't reach zero by 2050. And the UN aviation body forecasts that airplane emissions are going to triple by 2050. But then the ICCT just released a report saying that even that tripling number is conservative. It will be more than 1.5 times that. So there are still significant emissions that we're going to have to deal with in coming years. This is a graph from CARB showing that there will be use of gasoline vehicles for some time to come, even with their great work that they're doing on the light-duty sector. The road to complete light-duty fleet turnover is just going to be long and in some ways a little bit slow. So we need solutions for the interim. We want these light-duty vehicles that are in the dark blue portion of the graph to be operating on the lowest carbon fuel possible. So for all of the solutions that I'm going to show you, I want to point out one recurring theme that a wise woman advised me on, and that's optionality. We need solutions that are flexible, allow for multiple fuel and storage options, and can make an easy bridge from the technologies of today. Optionality will allow the market to find economic paths that allow us to retain affordable and accessible energy supplies. So on to aviation. Some companies are making big bets on sustainable aviation fuel, which is also called renewable jet fuel. For those of you that are less familiar, renewable jet fuel does meet all of the same ASTM standards and can be perfectly blended with fossil jet. You've probably actually already flown in a plane that has some percentage of renewable jet fuel and you didn't even know it. And that's part of the point, is that it's supposed to be that seamless. It's an exciting technology that's in a space where there are no viable near-term electrification solutions. Already there are major airports like SFO and LAX that are using some of this renewable jet fuel, which is why it's likely that you might have flown in a plane with some portion of it. So in addition to lower CO2 equivalent over the life of sustainable aviation fuel, some of its combustion properties are also improved so that it's also better for communities near airports. Since California can't regulate international and interstate commerce like that of aviation, SAF is only an opt-in credit generator to the LCFS, which is great. The value created by the LCFS is limited, though, in comparison to some other technologies. Jet fuel sector distribution and consumption patterns are just different than terrestrial fuels, and a lack of global book and claim is a hindrance to the very large investment that's needed for SAF. On to long-haul shipping. Renewable diesel is, in many senses, a really natural bridge for a lot of the existing oil refiners. It's taking a new feedstock, but a process that they're already familiar with and a lot of the same equipment, and it's producing a hydrocarbon fuel that meets all of the same ASTM specs. Just one point of differentiation, it is not biodiesel, it's chemically different. Those are two different fuels. There are some producers of renewable diesel already, including investments and tinkering by some of the oil majors. The Lawrence Livermore lab report that Sam was just talking about did identify direct air capture as a necessary third pillar to achieving carbon neutrality. And as Sam said, it's not enough to be zero. Technologies are going to need to be negative. And so that's where the direct air capture comes in. Also, there's ammonia and hydrogen, which are great solutions for heavy-duty applications like long-haul and marine. Those can be used in internal combustion engines or in fuel cells, giving some optionality pieces to it. The production of these fuels can have ancillary benefits like energy storage from surplus renewable energy. Hydrogen and ammonia do have to overcome the cost hurdle of being made from either lower cost natural gas or higher cost zero carbon electricity. And also the infrastructure and upfront expense of capital are key on all of these fuels, which is why it's so important to have policies that can help set different price signals. In some cases, electrification, even in light duty, has an especially long ways to go. This is the case in some rural settings where it will take considerable time and expense to build sufficient infrastructure that people are willing to switch over to zero-emission vehicles. So in this instance, I'm proposing that any combustion engines could become low carbon compatible. So for instance, if a plug-in hybrid were available paired with a mature technology like a flex fuel vehicle, you would provide a range of fueling options. The car could be plugged in and uses an EV for the miles possible. For the miles beyond the EV range, the car could run on E85 instead of gasoline. That provides carbon reductions now when they count the most, with a low-cost, already available fuel type. These would be a great bridge vehicle for people that just aren't really comfortable with making the leap to a full ZEV, which is true of some folks in rural settings for a variety of reasons, including topography and temperature extremes. Of course, the headwind to this is sufficient E85 fueling stations, but I feel reasonably confident that the infrastructure for this existing technology could get built pretty quickly if the policy signal sent to that market signal. So again, here, please hear and see the importance of optionality within the solutions listed here. I won't talk too much about the industrial piece since Chris covered this quite a bit. But what I will say is about one of the challenges that I have listed below, since there are many refineries that are probably going to still be operating in California in 2050 and beyond. We need solutions to help lower their carbon intensity, even if they are focused primarily on exports at that point. There isn't any LCFS value for exports, which means there is no incentive for those companies to lower the carbon intensity of those products. Cap and trade does provide incentive for refinery efficiencies, but that's really it. So I think that there's a little bit more consideration that we might have in that sector. So now I'm going to talk about just a couple of, just a couple of case studies to see how these solutions are rolling out today. The first is World Energy. They're a great company with several facilities across North America. One of them is in Southern California in Paramount, and they're producing a number of different renewable products. They're producing entirely renewable products at this facility. They're producing renewable jet fuel that is going to places like LAX and SFO. They're producing renewable diesel and naphtha, which is basically a gasoline replacement. They're working to scale the facility that they have, and once they are pursuing and have announced a large expansion of their Paramount facility. And once they are able to bring that to scale, they will be able to produce about 10% of the state's diesel demand. There's, through World Energy's pathways, there are a very clear set of ways that they're already exploring and have under development that can bring their fuels to carbon neutrality, and those aren't too far down the road. Another company that I think is very interesting is Carbon Engineering. They've been receiving quite a bit of pretty high-profile press, so that they're fun to read about. They are sucking CO2 out of the sky as a raw material, and that CO2 can either be geologically sequestered or used as a feedstock for renewable fuels, which gives it a lot of options. They now have a Texas commercial scale demonstration with Occidental Petroleum, but the market is still developing for direct air capture, as there isn't really a strong market value for geological sequestration compared to the large investment needed. And they did just make this exciting announcement into their supersonic jet work that they're going to be developing with Ariane. So now let's transition. I know that I've talked some about a few barriers, but I'll talk more specifically about some investment barriers. Many of these can be boiled down to unknown factors equals investor uncertainty, but they each have other impacts too. So questions about future market scale are always difficult to address. And the market access component of that means that if your demand is constrained in any way, then the reality is that new competitors could emerge and swamp your market. The example of that would be hydrogen charging stations. For example, there's pretty limited demand for hydrogen as a transportation fuel right now. And so that puts a real constraint on the actual market size. And so any competition in that space could wildly swamp the market that investors in previous facilities maybe didn't account for. There are also real feedstock limitations to some of these fuels. The feedstock and the renewable fuel companies are working to find other alternatives that are still low carbon, but for today, the challenges exist. And finally, in just the last 5 years, we've seen a significant federal administration shift on attitudes towards renewable fuels. This type of thing makes the steadfast investment that is needed in renewables all the more difficult. In terms of some other investment considerations, I wanted to show this chart from Goldman Sachs. What they found is that even promising technology applications like CCS, which is carbon capture and sequestration, and biofuels were hit hardest in the last recession. That's the area that you can see between 2008 and 10 in that gray, where you can see how the investment sort of stagnated for a little while there. We don't yet know how the COVID recession might impact renewable fuels, but it could stagnate our progress towards lower carbon alternatives. And finally, for a little contrast and to leave your mind on a point of intrigue, the same Goldman Sachs report has this chart of EU big oil companies' CapEx spending on low carbon energy. It's very interesting that in just the last 3 years, most of them have gone from less than 5% investment in low carbon energy to 10 or 15%. Now, US counterparts are not competing with this level of investment. Is this going to make EU energy companies more competitive in the future? We know the direction that California is heading, of course, but we don't know where the US as a whole is heading or the pace of that. So there seem to be two divergent investment philosophies. It's going to be really interesting to see which of these is the more lucrative investment portfolio in coming years. That's all I have for you today. Thank you very much.
All right, thank you, Mary, and thank you to all of our panelists for the informative presentations. We will now transition into the Q&A portion of the panel. So the way this will work, I will begin with a few questions for the panelists, and then we will open it up to our virtual audience to ask questions. And as a reminder, click the raise hand button to signal to the organizers that you'd like to ask a question. And there are over 400 attendees on right now, so I can't promise that we will get to everyone's questions, but we will do our best. All right, so I want to start off with a question for Chris. And I should just say at this point too, we strongly encourage any of the panelists to jump in and give their thoughts on these as well. We're just kind of starting them with particular people. So Chris, much of this morning's discussion focused on combustion of fuels, especially the last three presentations, but your work on industrial decarbonization has covered a number of non-combustion low-carbon technologies. So which technologies do you think have the most promise for heavy industry from both a technological and cost-competitive stance? Chris, I think you're still on mute. Hey, Chris, are you there? Ah, he cannot unmute. Let me fix that. Okay, Chris, try that again. Okay, Chris, we'll work on fixing that issue for you. I'm going to go ahead and jump to a different question. And in the meantime, Chris, try and unmute yourself with your own controls, and we'll see if that will work. Okay, this next question, this is really addressed to several of you. So several of you brought up feedstocks for renewable gas. So if we can't believe that we can electrify all end uses, then we will still need significant amounts of renewable gas. So what are the best feedstocks to produce this gas and meet this newfound demand? And Chris, we'll come back to your question after this.
Jordan, this is Sam. I'll take a first crack at that. You know, we really feel like you need to focus on the organic waste streams that society produces. And of course, you can attempt to reduce and reuse and recycle to reduce those organic waste streams, but they exist. They're significant, and right now they're mostly being landfilled. So we need to think hard about creating a circular economy and using those waste streams to help with our decarbonization challenges. And I tried to lay out in my presentation, the main streams that exist right now, including organic material into landfills, animal manure, wastewater treatment, forest residues, ag residues, from woody products, etc.
This is Janice. I would just add that I agree with Sam. Society's ills are also an opportunity, and we need to make use of them. And it may be locationally specific. There could be regions, say within California, where we have more ag waste, and thinking about circular use and the circular economy is how much can we reuse, repurpose for that local region. Like imagine a wildfire zone that has a lot of either ag waste or woody waste. Rather than just burning it in an open field, why not set up a modular gasification system to create renewable gas? That renewable gas can be directly used or further converted to hydrogen and used for backup to displace use of diesel and gas during, say, a PSPS event that's coming in the future. So I just wanted to add, I think there's a local and geographic consideration too.
Thank you both. Chris, let's go back to the question I asked before, and just to summarize that one, what non-combustion technologies do you think have the most promise for heavy industry? And anyone else is also welcome to jump in on this one.
Yeah, sure. No, that's great. California, I'm going to back up just a little bit. California is admired worldwide in my community because the transformative effects that CARB had on the vehicle market starting in the late 70s, early 80s, pushing to lower emissions vehicles, the initial try to EVs, which led to hybrids, what have you. And I think there's a huge potential here for California with the size of its economy and the size of both the private and public sector to establish markets for much lower GHG materials. So, for example, you might not make a lot of steel you do a lot of post-processing of steel products in the state, and you might not do a lot of primary. But if you help create the markets, if in AB 262, you've got most materials in there, including steel. The cement was unfortunately exempted. If you create the lead markets that reassure investors that it's worth putting money into decarbonizing steel, both primary and secondary steel. Potentially think about putting up a primary HDRI steel plant in the state, what have you. In terms of cementitious materials substitution, low carbon building, what have you. Now, it's not just the state that would do this. There's a lot of willing firms in the state. Tesla would be one that kind of comes to mind that help build those markets for low GHG materials. Be the place where global firms can come and sell, very low GHG steel, very low GHG cement, and at the same time, you can provide all the innovation support you need for your own companies to keep them competitive in that sphere. And if California does that, it's going to be transformative, because I know a lot of Canadian jurisdictions almost immediately follow California in terms of its vehicle regs and other ways of thinking, and the EU watches very carefully what's happening in California. So I think there's a lot of market-making potential for steel, for cement, in the longer run, chemicals, what have you, that as a non-combustion sort of low GHG materials leader. Anyway, that would be what I would say.
Can I just piggyback on that? This is Jess. What about low GHG almonds and avocados and all kinds of produce that we make here for local consumption and also export?
Yeah, absolutely. Fertilizer production is the largest chemical. It's the largest GHG intensity chemical there is. Making hydrogen essential across the chemicals industry, but making it for fertilizers is the number one sort of point source globally that you can identify. And if you can reset the standard to making fertilizer with green hydrogen, that would be transformative globally.
Great, thank you both. Janice, I'd like to ask you a question about the power to gas concept, and you touched on this with energy storage as well. You mentioned Germany and the EU recently releasing plans to scale up hydrogen production as part of their broader decarbonization goals. Do you see electrolysis of this scale working in California, and how do we get there?
Oh, absolutely. In fact, I think that the project you'll learn about this afternoon, the conversion of Intermountain Power Project, which is a very large-scale coal plant that's getting converted to a combined cycle that will combust green hydrogen made from electrolysis. That plant is at the same scale and, same timing as some of these large projects that are announced in Europe and Australia and around the world. What will happen as these plants are commercialized and there's now bankable demand for electrolysis equipment and green hydrogen production, the cost is going to come down. I think that IPP, although it's located in southern Utah, the primary off-takers are in Southern California, Los Angeles Department of Water, Glendale, Burbank. That single project will really put the United States on the map and open the door to many other applications of green hydrogen, because we'll have more learning, we'll have scale, we'll have procurement, and most importantly, we'll have momentum. And so I think that's the first step. What we need is some more projects demonstrating other types and other methods of producing green hydrogen. I know we have a large project in Southern California, the SMR of biomethane, and there are projects in the Central Valley that are looking for funding, largely supported by LCFS, to commercially demonstrate at a larger scale the production of hydrogen using gasification of organic matter. Oh, and your other part of the question of what will it take? Well, I'll go back to my series of recommendations. We can make this go faster. And I think the most important ingredient is leadership and focus, because hydrogen is so cross-cutting. It's this tiny molecule that can be it can be combusted, it can serve as storage, it can be put into a fuel cell and brought back to electricity, it can be used as an industrial ingredient. It's so cross-cutting across sectors. We really believe to accelerate progress, we need leadership, and we need one jurisdiction, one agency to stand up and serve as the EU of the United States. And we believe that the ARB is that agency. And, it's really, when you think about, boy, this little molecule, one of its advantages is it's so flexible. It can do so many things in so many sectors, but unless we focus on its potential and really coordinate the efforts of multiple agencies, progress is going to be tough, because it's human nature. We have our processes, our policies are all set up in a certain way, and what is that adage? What you focus on is what you get. So of course, it's much more complicated than that. There's a number of policies that need to be developed, a bunch of incentives and market mechanisms, but it all starts with leadership and focus.
Great, thank you, Janice. Mary, I'd like to direct a question toward you. You mentioned several potential uses for biofuels in a carbon neutral future. I want to narrow down on that a little bit. What sectors or what end uses are biofuels best suited for as a decarbonization option? And how do we scale up production and consumption of these biofuels to meet energy demand in those sectors where it's appropriate?
Jordan, I think my internet cut out for just a moment of that. So I think what I heard is just asking about how we scale up, and what was the other piece of it?
Yeah, that was the second half. The first half was narrowing down within your presentation. What do you say, I guess, what are the priorities for where we should be sending liquid biofuels in a carbon neutral future? What end uses are best suited for that?
Well, you know, the thing is that where the eventual places we'd like for those fuels to end up in the future aren't necessarily where there are revenue opportunities today. And so we can start developing some of those longer term market signals. I mentioned sustainable aviation fuel and trying to work on that market a little bit more. Of course, there's the industrial sector that has a significant need. But then the medium and heavy duty sector, I think that we overlook some of the applications where electrification may not be possible and where we do need other alternatives. And so some of the technologies that are intended for long-term use in those sectors aren't necessarily there yet. And I guess an example would be what I was mentioning with carbon engineering. You know, they've got this direct air capture to fuel, and they need to be producing fuel right now because that's where there's some revenue opportunity. They need additional revenue signals from policy, but a lot of people would really like to see them just doing the direct air capture into sequestration. And there's just simply not a sufficient revenue opportunity for that market currently. And so that they are going to need to pursue some other sort of interim technologies and pathways in order to get the investment together and wait for the policy signals to give those eventual market signals.
Thank you. And I would follow up with another question that several of you may want to jump in on. So Mary and Janice, you specifically both mentioned aviation as one end use that would be good for either liquid biofuels or for hydrogen. And even biomethane as well is another option for some of these long-haul freight vehicles. What's the best path forward here? There appears to be several different options.
Well, I'll start and let Janice pile on. At least for around the aviation sector, I think that we need to start thinking about some global book and claim policies. And we need at a global level to start thinking about how to consider the carbon intensity of renewable jet, or sorry, not just renewable jet fuels, but all jet fuels. And because there's essentially no policy around that, and all of the work that's happening there is voluntary. You know, that they do receive opt-in credits around the LCFS, which is fantastic, but that's only for California-bound fuels. So we need something that's a little bit more global in nature, which I know is a difficult task for CARB and California to take on. But you know, that's the honest truth of where we need to go within aviation.
Yeah, thanks. That's a great point. It's sort of in that spirit of what you focus on is what you get. And if we're not focused on it, we don't have a way of tracking and assessing the cleanliness of something. It's really hard to make progress. So the comment I wanted to make to your question is that innovation and industry is not standing still. So we have a fuel replacement, and there's many pathways to making an alternative fuel for aviation, as noted earlier by others. You know, hydrogen's a key building block, which we can make from renewable sources. But there's also innovation happening in the vehicles themselves. As I mentioned, Zero Avia is producing a short haul plane that is running on fuel cells. So we don't even need an aviation fuel. That solution, which is being commercialized now, can run on hydrogen, on green hydrogen, and it has a lot of benefits. It's super quiet. There's no emissions except water. So I think that, you know, the most important thing for all of us to do is to make sure that we preserve all pathways for finding low cost and viable pathways for producing renewable fuels. We need all of the above. We need to go as fast as we can. It's hard to predict which technologies are going to win. You know, I'm a big fan of Darwin. If you have competition and allow multiple pathways to flourish, that will produce better outcomes. And the last thing I wanted to say is that it's not only the technology, the in-use equipment like Zero Avia's new equipment, it's not only the production means of how do you make it, you know, we have to let innovation flourish on both ends, but on the transmission and distribution of these alternative fuels, we have to make sure that we preserve pathways and valuable infrastructure that may exist today and could be converted. And so I think it's worthwhile to say that the pipeline infrastructure that we have today, it's very valuable. And we have to think really creatively about ways to reuse that pipeline infrastructure for a cleaner purpose.
Can I jump in there?
Yeah, George. Yeah,
oh, sorry.
Go ahead, Chris.
I was just going to say there's a lot to there's a lot to unpack from what Janice is saying there. What is interesting going forward, I think what would be useful from the state and from CARB is some directionality on what are sort of the ultimate goals you want to be at, say 2050, 2060, 2070. And I would argue that we should not be combusting any sort of hydrocarbon near human beings by that point, because the health evidence that's just incredibly detrimental to children, to seniors, to what have you, it just keeps accumulating through time. So ideally speaking, if you're operating an energy carrier near people, it should be electricity or hydrogen by that point. However, that doesn't mean that there's a really important role for biomethane, for bioliquids and gases in transition, because we have so much equipment and infrastructure out there burning that stuff, using that stuff. To the extent that we can swap it in the near term, swap it out, keep all that stuff going, it's going to be critical. In the long run, though, we're going to be biomass limited. I'm not, you know, different regions have different ratios, but some places are incredibly high populations and low amounts of biomass available. And we need to be thinking in terms of conserving that carbon for CCS, for feedstocks, for chemicals, what have you, out, you know, sort of 20, 30, 40 years in the long run. What might help with all of this, coming back to Janice's point, is that in looking at our infrastructure, we have a gas infrastructure. Why not convert it to full hydrogen compatibility through time? Make it a priority every time that a gas pipe is dug up or a joint's replaced, that it's relined, resealed, such that it can handle a full range from full methane through to syngases through to 100% hydrogen, because it currently can't. It's somewhere between 5, depending on what part of the grid you're on, it can be 2%, 5, 15%, sometimes up to 30. So if we can rebuild that grid such that it can handle any mix of hydrogen, we're preparing ourselves for that space we need to be in a couple generations. So.
Yeah, and I'd just like to add, I mean, there is some path dependence and some technology lock-in that you have to think about, but policymakers also need to be nimble. I mean, the RNG industry was started with the idea that these projects were going to produce power, and then strong incentives were put in place for the transportation sector. So the resource started targeting that end use. But then recently, there's been significant push toward electrification of medium and heavy duty vehicles. So we're looking around to other opportunities as well. And policymakers and the industries need to be ready to shift as innovation occurs, both in their technology and in other technologies.
And one thing to add to both of those comments, which I agree with, is organic matter may be limited in absolute terms, but the production of hydrogen is not, when you think of the many, many ways to make it, including organic matter and from solar and wind, which is pretty unlimited. You know, getting to your original point, Jordan, that there is a limit to renewable, I would argue that there is not. With the technology we have today, we do have unlimited resources. And back to the earlier point about making the transition affordable, the only way we can make it affordable is by reusing the infrastructure we have to the greatest extent possible. And it's not just reusing the infrastructure, but it's also creating a pathway for economic development and job transition. It's not okay to tell whole populations that may have been, you know, involved in the fossil fuel industry to say, look, we're transitioning and you're gone. We have to chart a sustainable pathway so they can take part in this new clean energy future as well. And working with existing infrastructure is the easiest way to do that.
Thank you all. Yeah, and Janice, I'm glad you brought up infrastructure and the workforce, and that is going to be the focus of our second panel. So I'm glad that you have started that conversation. Let's go ahead and move to some of the questions from the audience. So just as a reminder, if you click the raise hand button when you're ready to ask a question, it will show up on my side as an organizer, and I will unmute you from my side and let you know when it's time for you to ask a question. So let's start with the name I see here is Chuck White. So Chuck, you've been unmuted. I think you can unmute yourself on your side. It says self-muted, and you can go ahead and ask your question.
Great. Hey, I hope you can hear me. Excellent presentations by everybody. The question I have is really more for Sam probably than anybody else, and it has to do with the CARB's clean truck rule, advanced clean truck rule that they seem to be developing now that seems to be really headed to primarily electrification by some point in time in the future. But they're beginning to roll out concepts of which types of fleets should be converted first. And interestingly, there was a recent proposal that refuse trucks should be converted over to electricity starting in 2026. All new trucks would have to be electrified. It seems to me that doesn't make much sense from the standpoint of being able to use renewable natural gas in the refuse fleet, which is the closest to be able to convert waste streams into renewable natural gas. And maybe some point in time down the road, ultimately refuse trucks will be all electric or all hydrogen, which is fine. But it seems to me right now for the foreseeable future, the best opportunity to expand the use of renewable natural gas is to divert the organic waste from landfills to reduce the methane emissions, and then to use it to power our vehicles that are most readily available to access that renewable natural gas. And I just wanted to get maybe Sam or anybody else's reaction to, it doesn't seem like it's really jiving with what a kind of a broader picture of what needs to happen. Thank you.
Yeah, thanks, Chuck. You know, I agree that for a long time was a very highly favored use of RNG that I think CARB and other people were very supportive of. And of course, you know, that has begun to shift a little bit. So that's what I meant when I said policymakers need to be nimble. You know, they need to adapt, and as they do that, they need to give clear guidance to these industries about what they should be doing, and then create the incentives that match that guidance, right? So it's not great to put someone on a path toward developing these closed loop systems with their waste fleets, and then suddenly say, no, you shouldn't be doing that anymore, and yank the rug out from under them to some extent. So I completely hear you and agree with what you're saying there. But you know, that's not to say that the end use of RNG in vehicles is the only long-term end use that the industry is looking at. We're in favor of all sustainable end uses and an optionality so that you know, as successes occur in other methods of decarbonizing the economy, the RNG resource is shifted to the sector that needs it the most. And that's just the advantage of being a flexible drop-in fuel that can use the existing infrastructure.
Okay, our next question will be from Sasan Sadat. Sasan, there we go. Go ahead and ask your question.
Cool, thank you. Yeah, I thought all these presentations were really helpful. One question that's prompted for me comes from what Mary was saying about the eventual sectors that we would like these fuels to end up in is not really where the revenue opportunity is today. And I'm just wondering if folks, I may have missed it if I stepped away from part of the presentation, so sorry if you have to repeat yourself, but what is the way that CARB and the market actors can sort of work together to move these fuels into these socially optimal sectors of decarbonization, like, you know, decarbonizing the existing use of hydrogen as a feedstock or in industry applications, rather than what we often see now, which is, you know, competing against end uses that we see a much more direct path to electrification, like in buildings and in like for low-grade residential and commercial heat, or for transportation, road transportation. How do we, I guess, leapfrog over those uses where there might be more revenue, but that we have lower cost decarbonization options into the harder to decarbonize sectors?
This is Mary. I'll start and take a try at that question. And it's hard to give a generalized answer to that because it is so specific to different technologies and different sectors. But within at least any given sector, it might require some policy support of interim pathways that maybe almost would seem to stand in contrast to CARB's stated electrification goals, but are actually in support of that, because what you're doing is helping support the short-term revenue of those companies and make sure that they have a pathway to be able to scale the technologies and continue the necessary development. And so it might require support of some of the technologies that CARB seems to be starting to move away from, and that includes things like biodiesel, which, you know, biodiesel capital can be turned around and used, as in the case of World Energy. It's primarily a biodiesel company, but they're using that biodiesel revenue to develop sustainable jet fuel and renewable diesel. So that biodiesel support is very important to that company. So that's just one example. I bet some of the co-panelists have some other answers as well.
Hi, this is Janice. I think your question is, what, if I could rephrase, is what are some of the ways that we can create bankability for these alternative fuels in the near term in a way that doesn't have adverse consequences and displace potentially lower cost ways of decarbonizing, such as building electrification? Is that your question, more or less?
He's been muted already, Janice. Sorry.
Oh, okay. Anyway, I'll assume that's the question. I'll answer with 3 main ways that can be achieved. One, consumer pull. We can make it cool to be green and low carbon from a consumer standpoint. And I think about, again, my super green avocado. As a consumer, I would probably pay a little more for that super green avocado if I knew it was made with green fertilizer. As a consumer, I tend to fly United Airlines because I know that they have a sustainable aviation fuel program. It's small, but I want to support them as a consumer. Avenue 2, incentives. The LCFS has been an incredibly successful program. Could an incentive program like LCFS be expanded to encompass more sectors and more applications? And then the third pathway that I've noticed has been very effective is through setting targets and mandates. You know, the target route is a little more palatable than the mandate route, but it is a very important market signal that going forward, this is what we're going to do. It worked very effectively for energy storage. Again, that was a target, not a mandate, and that there was a cost effectiveness out, but lo and behold, once we focus on it, we find that there are applications and uses that are more cost effective than even status quo decisions. So, and then, you know, underneath those under those three categories, there's a whole host of more detailed market mechanisms and policies like tariffs and interconnection rules that need to be sorted out. But all of it, I think the starting point needs to be prioritizing those applications where we can scale demand, aggregate demand for large procurements that can drive down costs. That's what's going to help us prioritize resolving the barriers and accelerating progress.
I'd like to throw one more thing in here. The UK has been at this file for about 15 years longer than most of the other English-speaking countries, and it's experimented with a lot of different, you know, innovation designs, policy designs, what have you, and it seems to have found something that's working for it. It's like its electricity GHG intensity is dropping very fast, and it has these targeted innovation programs that it uses to get the results it wants out of different sectors. And the one that always comes back to me, it's called the offshore wind accelerator. So they knew they had a tremendous wind resource around the British Isles in waters deeper than it was feasible to plant a turbine on the bottom. And they knew how do they access that at a reasonable cost per kilowatt hour. So what they did is they sat down with the turbine companies, and in an environment where, like, basically what they said was, we want floating turbines. How do we get those? And they working with the companies, they set out the supply chain to possibly get them. They kind of stretched it out and looked at where the technological issues were, and then with the companies, they invested in means to bridge those technological gaps. And it had to do with the floating platforms for the turbines. It was actually the ships to install and service them. And once the technological problems were solved, all the companies own the IP, and then they collapsed the program and sent them back into a competitive auction for kilowatt hour mode. So they have a way of doing sort of state intervention to get the results they want, and then pulling back into a much more normal sort of liberal competitive mode. And they've done this with a few different things. And I think ARB in California, possibly in cooperation with other very ambitious jurisdictions, could be doing things like this. What is the supply chain for key things that we want, like in terms of zero GHG heavy freight trucking, zero GHG jet fuels? Are there technological gaps? Can we cooperate on those to get the IP out there that we need, and then send the companies back into a competitive mode to provide that in the cheapest way possible?
Thank you all. Let's move on to another question. Bill Zobel, go ahead and ask your question.
Hi there, can you hear me?
Yes, we can. Good
morning. Speakers, very nice job, well done. I'm Bill Zobel with the California Hydrogen Business Council. Thanks for taking my question. I was intrigued by the comments of all the presenters, and in particular, Janice sort of touched on what I see as a strategic plan that she was working to put forward for everyone to consider, that includes advancing, green and renewable hydrogen into the economy. Janice, I'd like to hear your thoughts on, specifically where you think some ideas in market design might be put forward by ARB and some of the other agencies in the state, sort of the multi-jurisdictional approach that you touched on, that would help us get to there from here. And then secondly, we are of the opinion that a renewable gas standard in the state would help decarbonize the gas grid. Sam, I think you touched a little bit on that in your presentation. Other countries are doing that at what we consider extremely high levels, like 20%. California has yet to really get that started. Would love to hear your thoughts on that and where you think we can possibly go. And then Mary and Chris, lastly, on the transportation side, I think we've got a lot of opportunity in transportation, in particular if we look at the light and heavy duty sectors together and try to scale that. But I'd be interested to hear your thoughts on where you think we might be able to deploy some additional demonstration projects in the state that would help drive the technology forward. So actually 3 questions, but I appreciate your consideration. Thank you.
Thanks, Bill. Thanks. This is Janice. I think I had the first question, which is what are the ways that ARB can help move progress forward? And, you know, I talked about the importance of focus, and I'll answer your question by telling you a little story. I don't know, 15 years ago when we started working on energy storage of all types, we realized that it would be a really important addition to the toolkit just for the power sector. But it was a problem because until legislation was passed that created a specific rulemaking at the PUC focused on storage, it was really hard to make progress. Energy storage was already part of every, you know, we had a smart grid docket, the renewables docket, the long-term procurement planning docket at the PUC, and storage was in there, but it was like priority number 65. So in all these competing priorities within status quo dockets, it never quite made the grade. And with the AB 2514, which required the PUC to open a rulemaking focused on energy storage, engage with stakeholders, load-serving entities, industry, everybody, for the specific purpose of exploring applications, figuring out if it's cost effective, and if they found it was cost effective and viable, then to set a procurement target. The procurement target that was set was very small, but it was enough to get the engine going in a new direction. And that engagement process and the regulatory innovation that happened is what opened California's power sector to now routinely consider energy storage as a fundamental part of its toolkit, its integrated resources planning toolkit going forward. So that's what I talk about when I think when it comes to hydrogen, ARB can serve that role that the PUC's storage rulemaking docket served for storage 10 years ago. And the reason ARB is best suited to serve in this role is because its purview is beyond the power and gas sector. It spans all pollution, you know, air quality, and all sectors. And here we have a molecule, I'll call it the least common denominator that kind of touches everything, every sector. It needs that focus, it needs leadership to coordinate the activities and functions of all the agencies. Each agency has a role to help accelerate and think through the role of green hydrogen in our future decarbonized state, but it needs to be coordinated. CAISO needs to work on new wholesale tariffs and reforming their NGR models to have a new type of resource participate in their ancillary services markets. The PUC is doing great work in looking at injection and interconnection standards and what is the role of hydrogen. They're opening up a docket on the future of the gas system. There needs to be a focus on hydrogen because it touches all of the above. And clearly it would be in collaboration with these other key agencies. Hydrogen needs to be part of the CEC's IPER, Integrated Energy Policy Plan, and also the EPIC, RD&D funding. But because hydrogen is so cross-cutting across multiple sectors, it needs a guide, it needs a shepherd. And I believe that ARB is the agency to serve in that role. No pressure on you guys, but clearly we think you're super awesome-o. So that's what's needed, because until folks are focused, really focused, and putting appropriate energy and dedicating appropriate time, it's just hard to make progress. This is why Europe, you know, when they announced their hydrogen initiative and their hydrogen strategy, they created an actual body. I think it's called the European Clean Hydrogen Alliance. That's, again, it's a government, multi-sector, stakeholder, organizational capacity to make progress. We need to create the same here. I don't think this is going to happen at the federal level, but I think it can happen here under ARB's leadership.
Yeah, this is Sam. Janice, I completely agree. I think you know, a strong focus on decarbonizing the gas system is the last remaining piece of California's policy around greenhouse gases, and we have to begin to get that right. You know, certainly we think the PUC, the CEC, CAISO are all going to be critical agencies to have involved, but CARB needs to lead because it is fundamentally about greenhouse gas reductions at the end of the day, and they can shape what happens, you know, outside of the core customers as well. So, you know, we did support Senate Bill 1440 and got that through, and that directed the PUC to begin to take a look at a renewable natural gas standard. As Bill asked about, you know, we're still highly supportive of that moving forward. It's been a bit slow going at the PUC thus far, but we have a lot of hope that it's going to turn into something that can be a big driver initially for, you know, our industry, where the energy carrier is methane, and then in the long run to allow for this transition to hydrogen. So, you know, we see states like Oregon also getting out in front on this issue. They just recently passed a procurement program for their utilities for RNG, and that's extremely exciting to us. We want to see California prioritize it and get it right as well.
This is Mary. Going into the question about what kind of a demonstration project is needed. Gosh, my mind went all over the place of so many interesting demonstration projects that I would love to see across the state. But I guess I'll highlight one that I think would be particularly interesting, and that to me would be something like a refinery of the future. And this could be state funded. This could also definitely be funded within the private sector by perhaps some of the oil majors or a public-private partnership. But a facility that is taking renewable energy and utilizing that to produce hydrogen or ammonia to become process heat and feedstock, and using other renewable feedstocks to produce some of the liquid fuels for those long-term sectors that I flagged within my presentation that are necessary, and then have all of the appropriate recycling of chemical feedstocks and as closed loop of a system as possible, and just demonstrate how we can produce some of the liquid fuels that we're going to need on a more limited basis in the future in a way that doesn't have to compromise human health. And that same facility would have all of the appropriate carbon capture and sequestration technologies so that and other mitigation factors so that there are minimal, if any, effects on surrounding communities. I would love to see the refinery of the future modeled.
Thank you all. Let's move. Oh, go ahead, Chris.
Yeah, no, sorry. I was just going to say Mary's idea is fabulous. I've tried to pitch similar ideas to the Alberta provincial government a few times, and there are willing folks in the government, but it's kind of getting the political alignment on that. But that's fabulous. The one thing I have not mentioned, and I'm not as completely familiar with what's going on in California as others, is something as mundane as the spatial planning and allocation of sites for what have you for a hydrogen refueling network for heavy trucks. Fuel cell trucks have a huge potential to replace diesel trucks in the long haul. So it would be a hybrid battery fuel cell system. But before anyone's going to invest in those trucks, they need to know that they can fuel them. Private companies in the past have gone. Nikola talks about building its own fuel cell network, but that's insanely expensive and risky for a single company to do. There's been talk in the past of a West Coast, hydrogen refueling infrastructure from Vancouver to San Diego. If you're running a fuel cell truck, you can get more fuel one way or the other. But just things like that, just to lower the risk for new entrants to that sector.
Thank you all. Let's move on to another question. Allison Smith, you are free to ask your question.
Oh, hi, thank you. This is Allison Smith with SoCalGas. I wanted to thank the panelists and CARB for setting up this workshop. I think CARB has done a great job in constructing these carbon neutrality workshops. My question is for Mary Selecki. You had referenced a study that found that higher investment in renewable energy by the EU companies. I was curious if they highlighted any of the policy drivers encouraging this higher investment that could be applied to California.
It's been just long enough. I don't remember that. That was a Goldman Sachs study, and I would be happy to share through Jordan the link to that study. So get in touch if you need that. But no is the short answer. I don't believe that it was sort of an investment specific document, and they were looking at it through a pretty isolated lens and didn't necessarily take policy considerations into account. There's a lot of factors behind that difference in the EU and the US investment strategy. Some of it certainly is policy driven, and I think that actually it's probably more of a federal government related stance of, we've had such significant federal administration shifts and attitudes on things like a potential carbon tax or a cap and trade at the national level, that those kinds of shifting policy signals have been really difficult for U.S. oil majors to affirmatively say this is absolutely the direction that our government is going to go at this point in time, and so we need to get our acts together and make this investment happen now. Whereas in the EU, they are seeing those more consistent policy signals. Of course, in California, they do see those policy signals, and in the absence of seeing federal consistency, what we can do is take a more state-by-state approach, but of course that does have its limitations. I think there's other factors that are at play there as well, though. There's some cultural factors and just some comfort factors with, branching into different sectors that are outside of their areas of expertise and wanting to make sure that they're more responsive to shareholders. But there also is definitely, this is in part response to shareholder desires. And so the activity that we've seen by so many shareholder groups to demand more carbon accountability are having impacts. I think we're seeing those impacts in the EU first. And so if you're interested in seeing the US majors move in a similar direction, I think that shareholder advocacy is a really key way that we can help influence.
Thank you, Mary. Let's go to the next one. We have Ira Dasa. Ira, you can now unmute yourself and ask your question. Hi, Ira, are you there?
I am here. I apologize. So if I may, a question that picks up on something that Mary had said earlier about her desire, or her client's desire for a global book and claim approach. Sam, if I may direct this question at you, and I apologize, it's got nothing whatsoever to do with renewable natural gas, but rather picks up on the fact that there is a book and claim accounting approach for renewable natural gas under the LCFS, and I believe that was put in place under your watch. Would you be so kind as to explain to us how it works, and in particular, how it could work in the aviation setting? And if it helps, let's not think on the global scale. Let's just think about a book and claim domestically only. Thank you.
Sure, happy to put my old hat back on for a moment here. So the terminology is a little bit jargony, but basically what it is an accounting system to facilitate the recognition of production of a low carbon fuel that is less tied to tracing physical deliverability. And that is important in cases like renewable natural gas, where you inject the RNG into the pipeline system, the molecules are commingled, and there's really not a physical way to track where those molecules end up. So the system is really based around who helped pay to get that project built, what were the greenhouse gas benefits of that project, and then taking credit for those benefits, in California. So, conceptually, we certainly have strongly supported that for RNG. I'm not sure it's my place to speculate how CARB might want to approach that for aviation eventually. But obviously, for fuels that are critical to the long-term decarbonization pathway, it's helpful to have additional flexibility. And that's a method of providing flexibility.
Thank you, Sam. All right, let's take one more question from the audience before we give the panelists a chance to give their closing remarks. I have next on my list is Mike Kemp. Mike, go ahead.
Yes, thanks everybody for putting this all together. It's been very interesting. My question is really for Sam on the RNG from landfill gas. About 50% of the gas that you've extracted is CO2. Are there any special credits or anything better available to monetize that CO2? Thank you, sir.
Yeah, that's an excellent question. There's lots of things you could do with that CO2. You could sequester it. You could find electrolytic hydrogen and merge that with the CO2 to make additional methane, CH4. And there are some incentives within the LCFS that would promote that sort of thing. But we're really just at the beginning of seeing those types of technologies emerge and people getting excited about those options. It is an important part of the picture. Like if you can take a biological CO2 stream and sequester it, that's where you get the carbon negative performance from these fuels in the long term across all these wastes that I talked about. So the industry is very much paying attention and would love to see additional incentives to promote that smart use of that CO2.
Thank you.
All right, well, thank you to all of our panelists. As we wrap up this first panel, I'd just like to give you an opportunity to leave us with some brief closing thoughts. And let's go in the same order of the original presentation. So Chris, why don't you start us off?
I'd just like to say that California is in an interesting position that it is a state within a much larger federation. So it often, it's got its own goals. It's often thinking reflexively with the U.S. federal government, but it's also, I believe the fifth largest, as it by itself, it's the fifth largest economy in the entire world. It has a lot of market power in terms of, creating demand pull for clean fuels, for transport and heating fuels, for clean materials, what have you, and it ideally within its constraints as a state, as part of the U.S. Federation, it needs to think of that in terms of that and think about partnerships outside itself, with Germany, with the EU in general, with Canada, with the UK and others. There's a lot of potential there to literally transform the best available standard for doing a lot of these things in cooperation with those other jurisdictions. And California hits at that level, and ideally it should be thinking in those terms. So that's it for me.
Thanks, Chris and Jordan. This is Janice. I'd like to pick up where Chris left off and say that we are also an agricultural powerhouse, and lending from comments earlier about what the UK has done in terms of innovation clusters, I think there's an opportunity here for us to proactively think about vertically integrating our agricultural capabilities, bringing some of that fertilizer home, making that fertilizer green, and producing the super green avocado. And I'd just like to say that the other thing that California is blessed in, not just agriculture, but all these other sectors, is we are blessed with amazing progressive leadership in all our agencies, starting with our governor. And while the rest of the world is making really huge progress on green hydrogen, it's not too late for us be in that forefront. And I believe that with the projects that are underway, such as IPP and the leadership from ARB and the focus of this effort, we're going to be right up there showing the rest of the world how to get it done. And then the last thing I'll say is that the time to act is now, because this is happening. Green hydrogen is happening on a massive scale all over the world. And if we don't act now, we are going to be at a global disadvantage from an energy standpoint for decades and generations to come. So the call to action is now, and we have a window to be upfront, but we got to move. And thank you so much, and happy to follow up with anyone after this call if you want to discuss further.
This is Sam. I'd just like to say, overall, thanks for the opportunity. I do think CARB is looking at all of the right issues. From our perspective, addressing the gas system and finding a way to decarbonize it holistically and in a way that works well with existing fuel switching policies, like the low carbon fuel standard and the renewable portfolio standard, is a key goal, and it really needs to happen quickly. We've learned so much from successfully implementing those policies in the state. We should be able to quickly add on this last piece. If we don't, as Janice said, we're going to lag the rest of the world, and we're not going to benefit from the green jobs that come along with such technology. So it's the last key piece. We need to get started on it, and we need to move aggressively on it to reach our carbon neutrality goals. So certainly hope that there's a clear path for that after this workshop.
This is Mary. Of course, this workshop series is a precursor to CARB's scoping plan that's going to commence next year. And I'm so pleased for the focus of today's workshop. I think that CARB's on the right track in terms of some of the things that they are looking at and accounting for, and this scoping plan will be even more holistic and all-encompassing than its previous iterations. So very happy to see that. I guess the one piece that I would add in is that, I talked quite a bit today about some of the long-term focus that we need to have, but I want to emphasize that we shouldn't lose sight of some of the short-term technologies that exist today for immediate decarbonization. And yeah, some of them may not be some of the fuels that we want to achieve in the future, but we need carbon reductions right now. They count the most right now. And so wherever we can gain some of those carbon reductions today, seriously help us along our road and our pathway, and can help drive some of that longer term investment towards some of the pathways that we do ultimately want to see. So that's all for me, and really appreciate the opportunity. Thanks so much, Jordan.
Well, Chris, Janice, Sam, and Mary, thank you very much for the presentations and the discussion today. So we will now take a 30-minute break before we begin the infrastructure panel. We will return around 12:30. And the panelists, just a reminder to stay muted as we cannot turn off the broadcast. Thank you, and we'll be back in about a half hour.
Good afternoon. Thank you for sticking around for the second part of our workshop this afternoon. My name is Maureen Hand. I will be moderating this panel. This afternoon, we're going to talk about infrastructure and workforce considerations for the transition to carbon neutrality. The link that is shown at the top of this slide goes to our CARB, Carbon Neutrality Meetings and Workshops page. On this webpage, you can find the presentations that are being shown today. We will have a recording of the webinar that will be posted to the website as soon as we're able to. And we also have a comment docket open until August 5th. So we encourage you to submit written comments on the link at that website. If you would like to ask a question during the workshop today, please click the raise hand button here in the GoToWebinar. When we get to the question and answer portion of the workshop, of the panel this afternoon, I will unmute people so that they can ask their question. And let's see, so if you missed this morning's presentation, let me just briefly review our concept of carbon neutrality. So carbon neutrality requires balancing greenhouse gases emitted to the atmosphere with equivalent greenhouse gases removed from the atmosphere and sequestered. Our approach is to first strive to reduce emissions from all sources, including fossil energy, industrial processes, and natural and working lands. Secondly, we need to maximize sequestration through mechanical means, such as carbon capture and sequestration, or direct air capture with sequestration, but also in our natural and working lands. So this morning, we learned about the alternative fuels that are available to transition our economy away from fossil fuels. This afternoon, we're going to discuss corresponding transitions needed in our energy infrastructure. California has developed significant infrastructure to produce and move fossil fuels to our homes, businesses, and industries. Alternative fuels will require similar infrastructure because we still need to access this energy at our homes, businesses, and industries. We've got infrastructure to produce and move and store natural gas and other petroleum products. We have industrial equipment that is designed to use fossil fuels. We will likely need to modify this existing infrastructure or replace it with new equipment in order to best utilize the alternative fuels or to rely more heavily on clean electricity. Today, we are asking our panelists, how can we repurpose this existing infrastructure for a carbon neutral future? What new infrastructure is needed? And what steps can we take now to invest in a sustainable future? California's energy infrastructure is not solely physical hardware. The knowledge and skills to build, operate, and maintain these infrastructure assets resides in our workforce. As we consider transitioning to zero-emission energy sources, we also need to consider the workforce that will implement that transition. This figure shows the number of California jobs at the beginning of 2020 in 5 major energy technology applications. The fossil fuel-related jobs in the electric power generation and fuels applications are highlighted in gray with dots. The traditional transmission and distribution jobs are highlighted in gray with stripes. So the electric power generation sector has already experienced a transition away from fossil fuels to renewable energy technologies, and the workforce developed to support that transition. Alternative fuel-related jobs comprise only a small portion of the fuel sector, which still relies primarily on fossil fuels. And traditional transmission and distribution is now augmented with new applications related to storage, smart grid, and microgrids. So although new skills and knowledge will be needed for a carbon neutral future, much of the knowledge, skills, and experience in our workforce may continue to be utilized. Another key question for discussion today is how do we prepare our energy workforce for the transition away from fossil fuels to carbon neutrality? This afternoon, you will hear from several experts. Bethany Jones is the founder of Inclusive Economics, an organization that researches employment, economic, and equity impacts of energy transitions and climate policies. From the California Public Utilities Commission, we will hear from Gene Spencer, who leads a team working on issues related to gas policy and reliability. James McGarry will join Gene for the Q&A portion of the panel. James works on issues related to electric procurement policies and programs. Melanie Kenderdine is a managing principal of the Energy Futures Initiative. This organization advances solutions to the climate crisis through building coalitions, thought leadership, and science-based analysis. Greg Wynn manages the Los Angeles Department of Water and Power 100% Clean Energy Innovation Group. And finally, Jack Brower, the director of the National Fuel Cell Research Center at the University of California, Irvine, will join us this afternoon. So our first presentation will be from Bethany Jones. She's going to share some ideas related to workforce transitions for a carbon neutral economy. So Bethany, please begin when you're ready.
Oh, there we go. Okay.
Great, thank you. Okay, and now we see the slides. So please, go ahead.
Great. Thanks for bearing with me through the technical challenges. Maureen, thank you for inviting me to participate in setting up this workshop today. I'm really happy to share some of the thinking I've done around workforce transition with you all. I'm going to start just by providing an illustrative example. I've done a lot of work in the last couple of years looking at building decarbonization and thinking about workforce issues within that. So I'm going to start with that example and then talk a bit about high road jobs and end with a few ideas or principles around effective workforce transition. So to start, last fall, we published a report with UCLA, which was a jobs analysis looking at building decarbonization. And there's lots of things that need to happen to decarbonize buildings. We didn't analyze all of them. We did look at the energy efficiency retrofits required, all electric new construction, the electrification of end uses that are currently served by gas, and we looked at decarbonized district energy solutions for providing building heating and cooling. I'm not going to explain what that is now, although maybe it will come up later in Q&A. But though we only looked at these 4 actions, all of these things are necessary and they all have a place in decarbonizing buildings. And the workforce outputs would have differed had we expanded our scope. So what we found is that even with looking only at a single sector, which in this case was residential and commercial buildings, the workforce impacts touched several industries. There's construction impacts both in buildings and to build the new renewable capacity to meet that increased demand. There's potentially manufacturing effects if California were to invest in building out its manufacturing capacity to build things like heat pumps that are going to be required to electrify buildings. There's impacts in the utilities, positive impacts for electricity utilities and negative impacts for gas utilities. And then there's potential impacts on the fossil fuel side with the extraction and production of gas. And this is without even considering the ripple effects. So what happens and what are the job impacts of the increased costs of gas, and what are the other secondary and tertiary industries affected by the transition. But what I want to point out is that while these employment studies can get pretty granular in terms of the quantitative job calculations based on different scenarios, they leave a lot of questions unanswered, such as what is the quality of jobs created? What are the trades that will be affected by this? How can we create high road jobs or minimize or avoid direct worker displacement? And the rest of my short presentation will cover some of those questions and in a way, ideally that is applicable across the economy as the state moves to achieve its carbon neutrality goals. So I want to start with the question, not everybody's familiar with this terminology of high road jobs, although California is increasingly committed to this framework. First, I'll just say in the building sector, we did look at the job quality according to the industries that would be affected. And what we found is that somewhat surprisingly, given that so much of the gas use is in the residential sector, which is considered more a low road industry, I'll explain that in a second, about 60% or 3 out of 5 jobs created from the full electrification of California's buildings were in the high road industries. So this includes jobs in utilities, large buildings, district energy, and building the new renewable capacity to meet the increased demand. So why are those industries high road? In the high road industries, the characteristics are that competition is primarily driven by the skill, experience, and qualifications of firms and of their workers. And as a result, worker pay tends to be higher and turnover is lower. And in the low road sectors, competition is primarily driven by low cost. And as a result, worker pay tends to be lower and jobs are more precarious and there's higher turnover. This dichotomy, however, is not static. It's possible that high road jobs can become low road jobs and vice versa, that with intention, we can make even the traditional, quote, low road sectors more high road. So how might we do that? It really starts with intention and leadership. If we don't take explicit action to try to make sure that the jobs we're creating while we decarbonize are high road, decarbonization is likely to expand low road sectors and low road opportunities. And there's really three main reasons for this. A lot of the solutions around decarbonization are rather decentralized. It's a decentralization. You take rooftop solar, for example. It's decentralizing power generation. And as sectors get less centralized, there's not as much leverage around like collective bargaining or the other opportunities to ensure worker skill and worker rights and worker voice in the work. Two, lowest upfront cost has been a rather explicit goal of decarbonization efforts. And so there's been an effort to drive down costs, and that, as I showed on the previous slide, is a characteristic or a challenge that accelerates low road economic development. And third, and this is probably the most important, decarbonization is happening against a backdrop of wage stagnation and increasingly precarious employment and really a growth of low wage jobs. And it's really difficult to counter these trends with, especially when you're only looking at one area of work, which is decarbonizing the economy. And so it takes real political bravery, actually, to establish a high road development of the economy that's aligned with our decarbonization efforts. But if the leadership is there, then we know how to do this. There's sticks and there's carrots, and their application is rather vast. One thing that we can do is to tie incentives or subsidies or direct public investment to labor standards. So that might include prevailing wage standards or other wage floors, targeted hire criteria to make sure that those publicly funded or publicly subsidized projects are pulling in workers who might not have ready access or might have barriers to employment in high road jobs. We can also tie or use performance-based incentives to tie the subsidies or incentives to the quality of work performed, thereby showing support for a skilled and trained workforce. And then when you're not spending public money and you don't have that leverage, you can require strong licensing criteria and skill certifications and identify what the skill needs are as we decarbonize, and make sure that as we decarbonize, there's going to be jobs available for people who train in those areas and develop those skills. And then again, we can use enforcement to elevate the quality of work performed, and that also can support a skilled and trained workforce. So enforcing building code, enforcing labor and wage laws are things that can be done to support high road economic development and high road decarbonization. In addition, new thinking is required to support worker transition. We need to change our thinking from the lowest upfront cost as the optimal path to decarbonization to how do we achieve the best value? How do we get more out of our upfront investments? And that might lead to different solutions than if we're only looking at lowest upfront cost. We need to change our thinking, especially now, from the idea that any job is a good job to no one wants or no one deserves a bad job. We need to make all jobs better. And right now we need jobs, but then a lot of people respond to that thinking in terms of investing in training. And training can prepare workers for jobs that exist, but it doesn't create jobs. So we need to shift our thinking around needing jobs to needing good jobs, and how can we proactively invest in and develop new high road industries. We need to move away from the idea that there aren't all that many fossil fuel workers in California that will be affected, not relative to the whole state workforce, but recognize that behind every single job loss is a person, and often a family, whose livelihood is dependent on that work. It's not just a numbers game. And we have to go from the thinking that jobs matter and the more the better, to really thinking harder about what types of jobs are we creating, what is the quality of those jobs, how are they protecting workers, and where are they, and how are they distributed throughout the economy. And then to provide a little bit of guidance on workforce transition. I think often when people think about transition, they jump immediately to thinking about retraining fossil fuel workers. And that's important, but it's only one piece of the puzzle. And in part because it's better to avoid worker displacement, avoid the need to retrain in the first place. So a few things that we could get better at here. One, comprehensive solutions. How do we engage in comprehensive industrial planning to support new high road opportunities and new industrial development in California? And there's no single solution. We really need to do demonstration projects, try a lot of different things, and see if we can build out the high road economy in the state. Two, social dialogue, sometimes also called in some parts of the world tripartite planning. But this is, and because I'm talking about workforce here, I'm not including like community stakeholders, which are also really important stakeholders in a transition discussion. But as it concerns workforce, engage with affected worker representatives and honor the collective bargaining relationships that they have with their employers, and that the transition needs to take place in the context of those arrangements. Three, we really need to assess the skill requirements, map the skills needed for decarbonization against the skills that we have already in the fossil fuel industries and infrastructure, and ensure then that we have an adequate workforce, both for maintaining the safe operations of fossil fuel infrastructure as these industries are in decline. It's tough as a worker to stay with a dying industry. So how do we retain a skilled workforce? And then how do we identify solutions that are closely aligned with some of those same skills and occupations? Fourth, I think we need to do better jurisdictional planning and coordination, align efforts between state and local government, recognizing that this state is incredibly diverse and one size will not fit all, and we need to try a lot of different things. And then finally, of course, we do need to think about financial resources to support worker transition. And the sooner we start, the better. It can be expensive to do this right, and we need to start planning for that. All of these things really need to happen in the context of long-term planning. This is not going to happen overnight. It's better from the workforce perspective, for sure, to avoid industry destabilization or the so-called death spiral, avoid worker displacement, retain workers to safely manage the energy transition. So in closing, I'll just say we still have time to do this right. We have 25 years till 2045, and we have the resources in terms of the analytical ability and the willing engagement of stakeholders to really get this right in California. And I'll leave it at that and put up my contact information while we're waiting for the next presenter. Thank you.
Thank you, Bethany. That was a very useful discussion about the workforce. Our next presenter is Jean Spencer. And Jean is going to talk to us today about some insights related to transitioning energy infrastructure, particularly the natural gas and electricity.
Okay, can you see my screen?
Yes, and I can hear you.
Perfect. All right. So I'm Jean Spencer. I'm the supervisor of the Gas Policy and Reliability section at the California Public Utilities Commission. And I'm going to be presenting some slides for James McGarry from the Integrated Resources Planning team, who will be here to answer questions during the Q&A. So the topic of our presentation is Getting to the Future, Infrastructure and the Energy Transition. Okay. So I think we all agree that California's goals require a transition away from natural gas or from fossil gas, but we can't get to the future without getting through the present. And today, California's electric system depends on gas for reliability. And there's two key times when the electric system really depends on gas. During the intraday ramp, which is depicted here, this is a recent graph from the CAISO. You can see this was a day with a really high level of renewables through much of the day. But as they start to fall off, you know, between 4 and 6, then gas starts coming on. That's the orange line. Imported electricity comes on, and large hydro. So gas is providing an important backup service on the intraday. Another period when gas performs an important function for the electric system is during the Dunkelflaute periods of winter. And Dunkelflaute is just a fun German word for dark, windless periods. And these periods tend to occur most in January, which happens to coincide with the highest residential heating demand of the year. So the takeaway there is that even if we are able to electrify everyone's homes, we'll still need to get that electricity from somewhere. And if you take a look at these graphs showing hourly wind and solar generation in January and June, you can see that in January, for hours at a time, there's 0 or near 0 solar and wind generation. And these are longer periods than can be met by a 4-hour battery. So at this point, you know, under our current circumstances, gas fills in. So in the context of this transition to renewable resources, we also still have to maintain the CPUC's traditional mandate to provide safe, reliable service at just and reasonable rates. And that means that the gas infrastructure must be maintained and kept affordable for as long as it is needed. And one of our challenges at the PUC is that the state's gas infrastructure is old and in some cases in need of repair or replacement. So these photos show a ruptured pipeline and another pipeline that has pitting from corrosion. A lot of our high pressure gas transmission pipelines were built 50 to 70 years ago. And not all old pipelines are problematic, but your probability of having a problem goes up over time. There's just more time for something to go wrong. And some recent examples of pipelines gone wrong were the 2010 San Bruno explosion and the more recent explosion of Line 235-2 in the SoCalGas territory. To the right is an excerpt from a recent GRC. And these are some pipelines that the utility was asking for money to repair or replace. And you can see that the vintages go back to 1928, and there's kind of a cluster from the late 40s to the 50s. So from the PUC's perspective, we have to decide whether to act or not to act. Do we authorize funds to repair and replace these old pipelines, or do we not? And that, again, you know, our mandate is safe, reliable, and just and reasonable rates. So we also need to be thinking about avoiding stranded costs. Stranded costs occur when, for example, if you think you have 50 years to pay off a pipeline, but you end up taking it out of service after 20 years, you have to make up those 30 years of payments in relatively short order, which can cause rate shock for ratepayers. So these are some of the issues we're looking at in the long-term planning gas OIR that was open this year. We had one workshop about it last week, and we have another one next week if you'd like to join us. Okay, so here's some things that we're seeing as we look at the gas system. First of all, overall gas demand is decreasing. Summer peak demand is decreasing. But our recent forecasts show winter peak demand being essentially flat between now and 2030. So as far out as I've seen so far. And the reason for that is less electricity is available for import as our neighboring states move away from coal and towards gas and renewables. So during those Dunkelflaute periods of winter, they're going to need their electricity for themselves, and they won't have that extra coal-fired power that they can export to us. The reason this is important is that gas infrastructure is designed to meet peak day demand, and winter is the gas peak. So if the winter peak demand is not changing, that suggests that we will not be able to change our gas transmission infrastructure very much, at least within the next 10 years. So what can we do in the near term? E3 has suggested that we focus on distribution. This is an excerpt from one of their reports. And I think this is a very sensible suggestion. Distribution is the largest portion of the system. It's the most miles of pipeline because it has to serve all the different homes and businesses. And they suggest targeting electrification to specific neighborhoods so that you can either not build the gas infrastructure to start out with, it's a new neighborhood, or you can take out of service the existing gas infrastructure and only have to maintain the electric infrastructure. So on its face, this makes a lot of sense, but there are some challenges to executing it. One of them is that the utilities have an obligation to serve. So right now, it seems as though if there was one neighbor in this neighborhood that wanted to keep their gas stove, then maybe you would still need to maintain that gas infrastructure. So this may be something that the legislature needs to take a look at. Another thing we're finding as we kind of dig more into the details is that the jurisdictions with the most political will to electrify are not necessarily the places where old or problematic pipelines need to be replaced. So to make the most sense economically, the best thing to do would be to target neighborhoods that have old pipelines or problematic ARB-led pipelines that you wanted to take out anyway, and then just electrify, and then you don't have to replace those pipelines. But those places tend not to be Berkeley or other cities that have expressed an interest in electrifying. Okay, so now I'm moving on to James's slides. These images are from the CEC, and they show the deep decarbonization trajectories for meeting the statewide 80% GHG reduction by 2050 goals. The one on the left shows 3 different scenarios for meeting the goals: a high electrification, high biofuels, and high hydrogen scenario. And one thing to note about that is the energy level, or the total usage of energy, is fairly similar across these 3 different pathways. It's just the mix of resources that changes between the 3. The image on the right zones in on the high electrification panel or scenario. And things to notice about this is that first of all, the energy demand is declining really rapidly between now and 2050. And then if you focus in on the dark green shaded area, which is the fossil gas use, you see it starts to decline pretty significantly in the mid-2020s as it's replaced by renewable gas and electrification. Okay, this slide is from the Integrated Resources Planning team at the PUC. And it was developed using the RESOLVE model, which is looking at what needs to be built to meet the SB 100 goals of 100% carbon-free electricity by 2045. And it chooses the least cost portfolio to meet supply and demand and meet the goals. So, as you can see, there's again the 3 scenarios: high electrification, high biofuels, and high hydrogen. And under each of these scenarios, it's the yellow and purple that jump right out at you. And the RESOLVE model is picking solar and batteries to meet these goals. And it's picking a lot of them. Another really important thing to note about this is that this represents 150 to 190 gigawatts of new renewable energy and storage technology that must be added to the system. And that's in contrast to the 85 gigawatts of installed electric generation capacity in California today. So that's a really big lift to go from 85 to 190 potentially. It would require 6 to 8 gigawatts of new capacity growth per year for the next 25 years. And again, to put that in context, our current record for installing new renewable energy is 4 gigawatts in 1 year. And it would also require potentially up to 85 gigawatts of new transmission capacity, although there may be some non-wire alternatives that we could pursue to bring that down. So this is a preliminary analysis, but I think it is just important to note the scale of what would need to be built to meet these goals. The last thing I want to point out about this slide is this gray shading here at the bottom. And that is the gas-fired electric generation capacity that is not retained. And the thing to note about this is that there's not much that's not retained. Our current models are showing that almost all the gas-fired electric generation capacity will need to be retained to meet demand peaks and to fill in when wind and solar drop. So that leads us to some kind of challenging questions, because if we still need to have gas-fired electric generation on tap when we need it, that means we still need to maintain the gas transmission system, and we also need to come up with a market structure that will support these electric generators that get very little revenue from energy sales. And those are some of the issues we're struggling with and trying to work through at the PUC. And that's it for me.
Thank you, Jean. That's a lot of infrastructure capacity that is very complicated. Let's see, our next panelist is Melanie Kenderdine. So Melanie's going to share some observations about repurposing some of the fossil fuel infrastructure. And Melanie, we're ready when you are.
Thank you so much for asking me to share a few thoughts with you. Thanks to Maureen for the invite. And as I said, I give the speeches all the time. I'm just getting used to the video variety. I hope I can make it through these slides without technical difficulties. I wrote that before I started. It's too late for that. So I also hope that your families are safe and healthy in these difficult times. As some of you know, EFI did a study of deep decarbonization in California and identified technologies that could help California meet its 2030 and mid-century goals. We saw technology pathways. There were 33 of them. If you met all of them, did all of them precisely right, the state could meet the 2030 goals. We did not see a set of technologies for California to meet its 2050 goals. And the importance of innovation comes in when you look at that. And I'm going to spend a little time amplifying some of the longer term opportunities that deserve policy focus, both policy focus and innovation investments. And I'm going to add a little something, listening to the previous presentations. Maureen used a slide from we do an energy jobs report each year. And I have looked at those top 10 states in the country in a range of fields, comparing them to top 10 in unemployment, and looked at top 10 jobs in a bunch of categories. California is number 4 in the country in oil and gas jobs, fuel jobs. It is number 1 in efficiency jobs. It's number 1 in gas generation jobs, number 1 in solar, and number 5 in wind. So what we have done, we've done a crosswalk of existing carbon infrastructure across the top to support decarbonization pathways. People have mentioned that before, opportunities there. So we've got oil refineries, gas processing. Could you click, please? Click twice. There you go. Okay, so oil and gas refineries, natural gas generation, oil and gas pipelines, ports, and storage. So those are your conventional energy jobs and our infrastructure. And then over on the left, you see biofuels, hydrogen fuel, or feedstock. Click again, please. And then going down that, negative emissions technologies, that's CCUS, renewable gas, we've talked a lot about that, and smart systems and platforms. And to just give you a few examples, okay, of where we see substantial crosswalking, between conventional energy jobs and clean energy jobs. Hydrogen co-firing, we've talked about that earlier, can be used in gas generation and gas pipelines. Natural gas expertise can be used for energy storage. As I mentioned, hydrogen can be used in existing pipelines, but it's limited. You can use 15% in pipeline volumes with minor upgrades. Oil and gas, it can be used in CCUS technologies. The expertise and workforce is very, very similar. A direct air capture, somebody talked about that earlier today. You need sequestration for direct air capture. So there's a pretty significant relationship between direct air capture and carbon storage. Biofuels can be used in existing fuel infrastructure for fuel storage and transportation hubs. Renewables gas processing, very similar to natural gas processing. And smart platforms can create smart generation solutions, for example, managing natural gas and battery hybrids. Click, please. Our conclusion was that decarbonization pathways are as much about infrastructure as they are about technology. The transition to a low carbon future could potentially be improved by seeking opportunities to leverage California's existing physical and intellectual infrastructure, technological expertise, and its skilled and ready workforce. Next slide, please. So what you see here, we have, this is a cartoon of how a hydrogen hub could be used at the ports of LA and Long Beach. Hydrogen produced from gas-fired steam reforming with CCUS and electrolysis. You can see down in the lower right-hand corner, you've got steam methane reformers for producing hydrogen from gas. And then over here in the middle up above, you've got electrolysis. Electrolysis is, however, 4 to 5 times more expensive than steam reforming. And that is 4 to 5 times more expensive than gas reforming of hydrogen with CCUS. So there's a lot of work in bringing the cost down there. And then what you can see, you're using the natural gas, retail gas, you've got onshore sequestration, you've got hydrogen storage there. You can use that in petroleum refining, you can use it for ships, you can use it for trucks, and you can use it for power generation. So click, please. Okay, one central steam methane reforming facility and one central electrolysis facility that you see there, it could supply half of the port's drayage fleet. That's your trucks and your forklifts, et cetera, et cetera. The entire port's electricity requirements, that's 50 megawatts an hour. 80% of the petroleum refiner demand there, 10% of residential gas demand, that's as a blend with gas, and CO2 sequestration equivalent to half an average coal plant emissions. So that's the hydrogen hub, the infrastructure you would need, and how valuable it could be to just run a port or a couple of ports. Next slide, click, please. And just last week, the International Energy Agency in Paris put out an innovation study. I encourage people to look at it. They focused on basically 3 things: decarbonizing electricity, technologies for that. They focused on hydrogen infrastructure and on CCUS. And they've got stages of development. I have a little bit of disagreement with some of those stages. Click, please. There you've got the colors there: mature, early adoption, demonstration, and large prototype. And because this is about infrastructure, I focused on the infrastructure here. They've got a whole lot of areas, but infrastructure. Click, please. And you've got, there you see pipelines and tanks are mature. You see those that are in early adoption, a demonstration, and large prototypes. Click, please. And so I would think California has a strong interest in hydrogen incentives, perhaps a loan program, and also innovation programs. So next slide, please. This is potential carbon sequestration sites, and California has excellent options. You've got mostly saline formations over there. You can see in California some oil and gas reservoirs. When we did our study of technologies needed in California, CCUS figured heavily into success for electricity industry, and I put transportation in there because the LCFS is important for CCUS as well. It's considered to be a critical technology for reducing emissions around the world. The UK is the first European country to adopt net zero emissions targets. This is a quote from their net zero plan that they put out recently. Quote, carbon capture and storage in industry and very likely for hydrogen and electricity production is a necessity, not an option. In our study that I mentioned earlier, 3 of the 33 technology areas that you see highlighted there on the slide get you 34% of the emissions reductions you need in 2030. So 3 of 33 categories in those areas with CCUS would get you 34% of the way to meet your 2030 goals. There's also a 45Q tax credit for CCUS. And I would say one other thing, it provides a perfect opportunity to put the associated skills to work from oil and gas and to mitigate carbon emissions. California has about 100,000 workers in oil, gas, and pipelines. These workers could support an entirely new industry in CCUS. And this is underscored by IEA in its sustainable development scenario, which says that over 2,000 CCUS facilities would be needed to be in operation by 2050, employing a huge number of workers. It would also create a global market if California is a leader there. And I want to just a data point. In 2018, 2 countries alone in the world, India and China, had 164 megawatts of coal under construction, not announced projects, but coal plants under construction. The entire US coal fleet is 235,000 megawatts. So 65–70% of the entire US fleet under construction in China and India in 1 year. They're going to need CCUS technologies. It would be great to be a leader there. Next slide, please. This is an innovation heat map. We did a clean energy innovation study earlier in 2019. We released it in early 2019. In this heat map, and you can see from purple to sparse, yellow to dense, red and yellow to dense, California, very, very dense in clean energy innovation on our index. Included in that index is DOE laboratories. You've got 2 of them, energy innovation hubs, FFRDCs, manufacturing centers, NASA labs and facilities, and the top 100 research universities are in there. So California has a very significant clean energy innovation infrastructure. Click, please. Okay, I'm sorry. If I clicked it myself, I would have done better. So next, click, please. Okay, in that study, we identified what you need to do to identify breakthrough technologies. So first is analyzing key drivers of clean energy technology breakthroughs. Next, click, please. Just click through this. Keep clicking. There we go. There you go. Stop there. Developing selection criteria. That's technical merit, market viability, compatibility, and consumer value. Identifying the universe of emerging technologies. Identify innovation areas with significant breakthrough potential. And remember, I said California needs breakthroughs to meet its 2050 goals, and it needs to do everything right to meet its 2030. So click, please. And these are the critical innovation areas we identified. Storage and battery technologies. I know you all are very high on batteries. California had 90 days in 2017 with no wind. it had 11 days with no wind, 11 days in a row with no wind. Battery storage is max 4 hours, so it's lithium-ion batteries. Advanced nuclear reactors, I know you have a policy to not build any more reactors until the waste problem is solved, but that's an area where you could get emissions reductions. Applications for industry and buildings, difficult to decarbonize, and that's hydrogen, advanced manufacturing, building technologies, then systems, smart grids, smart cities, and then again, large scale carbon management. Click, please. And then one last issue I want to talk about. This is USGS data. I mentioned batteries. World Bank did a study of the metals and minerals required for wind, solar, and batteries. Not surprisingly, most of them are not in the United States. Click, please. Click 2 more times, okay? This is just to show you volumes of lithium, okay? 8 million, these are in metric tons, 8 million metric tons of lithium in Chile, 2.7 in Australia. The United States has 35,000 metric tons of reserves of lithium. Cobalt, US 38,000 metric tons. Click, please. Congo, Democratic Republic of Congo, not exactly a stable part of the world, 3.4 million metric tons. I would say one other thing about those mines. There are 18 cobalt mines in Congo. 14 of them are owned by the Chinese. Australia, 1.2 metric tons. Click, please. You can vary the volumes of cobalt and nickel in a lithium-ion battery, and Elon Musk, because of the working conditions in Congo, wants to use more nickel, less cobalt. So I looked at nickel as well. US has 110,000 metric tons. Indonesia has 21 million metric tons of nickel, and Brazil 11 million metric tons. Click, please. Meeting the clean energy ministerial's target of 30 million EVs sales in the world by 2030 would require almost 3 times the current level of cobalt for all uses. At these rates, reserves would last 23 years. Click, please. This is a conclusion from the World Bank study I mentioned. All literature examining materials and metals implications for supplying clean energy technologies agree strongly that these are material intensive, that would much more material intensive than fossil fuel mechanisms. Simply put, a green technology future is materially intensive, and if not properly managed, could belie the efforts and policies of supplying countries to meet their objectives of meeting climate and related sustainable development goals. Click, please. My conclusions on that: the US should increase its diplomatic and investment focus on Western Hemisphere and Africa, protect the supply chains for the minerals and metals needed for wind, solar, and batteries, support new domestic environmentally responsible mining activities for key metals and minerals, support innovation in mining efficiency and in earth abundant materials for wind, solar, and batteries, use renewable electricity for mining. Next, promote humane mining conditions around the world. And click, please. Start metals and minerals recycling programs now. And I'm going to close with just a couple more factoids on this issue. And the reason I put this here, I was crosswalking skill sets, et cetera, et cetera. The oil industry is one of the few truly global industries. Along its supply chains, it passes through different legal frameworks. It includes activities such as domestic and international transportation, ordering and inventory visibility and control, materials handling, import-export facilitation, and information technology, which we will need, and I'll give you the factoids now, because the World Bank looked at 21 categories of metals and minerals. Rare earth, everyone thinks this is rare earths. That's not the case. Rare earths are one of those 21 categories. China was #1 in 11 of those categories as a resource holder, and Australia was #5. I had 5. So 15 of 21 categories, the resources are largely in China and Australia. Supply chains, energy security issues become very helpful, as does recycling becomes very important. Domestic mining, reinvigorating some of that. A lot of copper in wind turbines, a lot of copper in an electric vehicle. And we have a lot of closed mines, copper mines. I'm in New Mexico today. We've closed most of the copper mines here. So it's an important issue we need to pay attention, and thank you very much. I'm sorry I went over time. Thank you.
Thank you, Melanie. That was a lot of great information. A lot of things to think about there. Our next presenter is Greg Wynn. And Greg is going to talk to us about a specific power plant that LADWP is working with. Please proceed, Greg, when you're ready.
Okay, great. Thank you. Can everyone hear me okay? And everyone can see my screen?
Yes. Yes.
Okay, great. Thank you. Thank you for the opportunity to speak today. I'm excited to showcase this project, something we've been working on for quite a bit of time, and I think it's great that we can finally show off how we're taking an existing power plant, a coal plant at that, and change it into something that would be extremely beneficial and a showcase to how we can get to that clean energy future that California is looking for. The project that I am speaking about is the Intermountain Power Project. Just to start off, this is what the current Intermountain Power Project looks like. If you've seen anything about this project, the IPP, you'll typically hear people refer to this as the Intermountain Power Plant, but it's called a project for a reason, because it is more than just a power plant, and I'll get into that in a little bit. The project itself is located in a part of central Utah called Delta, City of Delta. It's currently 2 coal units, 1,800 megawatts of net capacity. It's been operating since the mid-'80s, since 1986. And this is the part where I refer to this as the project. IPP consists of the generating unit, the 2 coal generating units, but it also consists of 2 very large transmission systems that I'm going to highlight today. The northern transmission system that moves power through Utah and Nevada, and also the southern transmission system that takes power from the Intermountain Power Project down to California. Currently, the northern transmission system is an AC system, alternating current system. The southern transmission is a 2,400 megawatt direct current system. Again, that brings power from the Intermountain Power Project in Utah down to Southern California. It's currently has some renewables flowing down the southern transmission system. We have currently 300 megawatts of wind interconnections. Even though I am from the Los Angeles Department of Water and Power, the project itself is a partnership between some organizations in Utah, the municipal utilities out there, and 6 Southern California municipalities in Southern California, namely Anaheim, Riverside, Pasadena, Burbank, Glendale, and the Los Angeles Department of Water and Power. So it's a partnership. It's a very good partnership that's been very valuable to us throughout the decades. The current coal project that we're looking at is slated to close in 2025. We're going to be shutting down the coal units and bringing up these new natural gas units that will have a bit less of the operating capacity. We're looking at a new power plant of 840 megawatts. This is, again, a natural gas powered facility. The northern and southern transmission systems will remain, but the southern transmission system will also go through an upgrade as well as part of this new project. So that right now is just to set the table as to what the current project looks like. And as I go through this, we're going to talk about how it is that we're going to change what we had as a coal plant, change it into a natural gas plant, and then with the vision of getting it to become a hydrogen-fired power plant that will get to our goal is to get to 100% fuel mixture of hydrogen, green hydrogen, into that power plant. So the reason why we think it's possible here at the Intermountain Power Project is that for a couple reasons. And one of the big ones is that if you look at the map on the right, where that star is, that is central Utah, and that is where the Intermountain Power Plant currently sits. And you can see there that it sits in an area that has a lot of accessibility to renewable energy, different types of renewable energy. We have wind from Wyoming, Montana, we have solar, Arizona, New Mexico, Utah, California. So there's some geothermal out there. So it really does sit in a very good spot so that there is an ability to utilize that renewable energy. And as I go through the presentation, you'll see why that's important. Not only to bring some of that renewables into California to serve load, but also will have a different application. You'll see that in a minute. Currently, like I said, we have over 300 megawatts of interconnection for wind. Right now, we have in our queue 2,300 megawatts of solar and potentially more 1,500 wind from a potential Wyoming project that we're in current discussions with. So when we look at the projects as a whole and why this makes sense, I talked about renewables. I talked about the transmission systems that we have. In addition to those other resources, we have an abundance of land and water in the area. The power plant itself sits in a rural part of Utah, so there's plenty of land. And when the project was initially put into service, we were able to acquire a large amount of water rights in that area as well. The project also currently sits on a unique geologic formation. It's called the salt dome, which is ideal for storing gases. They're in the United States. They're typically located near the Gulf of Mexico area, but we are fortunate enough to be sitting on top of one of the rare ones in Utah. And of course, nothing can be done without our great people. We have amazing staff, technical staff, operating staff, experienced people who've been running in the power plant for many, many years. I think we can still utilize the expertise and the people that we have there currently. So again, setting the table for what I'm going to be talking about, we have the renewables, we have transmission, we have land and water, we have this unique geologic feature, and then trying to put that all together. It will really help us get to this green energy future with green hydrogen. So as I spoke about earlier, we are transitioning from a coal plant into a natural gas-fired unit. We went through an RFP process. We were able to award. I'm sorry, let me go back one. Not too far. We were able to award to Mitsubishi MHPS, and they're going to be providing us with the generator and the turbines for the new project. As part of the RFP, we had asked for what the capabilities were on these new generators, and the generator that was selected was one that would be able to burn a hydrogen fuel mixture starting day one of commercial operation. So starting right off the bat in 2025, we'll have, of course, with some modifications to the infrastructure, we'll have the ability to burn a hydrogen fuel mixture in those turbines starting in 2025. So in addition to that, we also have an ability, because of that unique storage feature that we have, the salt dome, we do also have an ability to store some of that hydrogen fuel that's going to be created by this project. This is, I think, one of the most unique portions of this project, because it's one thing to be able to create the hydrogen. The other part of it is, and I think one of the important parts that was highlighted in the previous presentations, was that how do you store that energy? Storage is going to be a huge component in the future, and looking at what we can do at the Intermountain Power Project, we can create the fuel that will run the generators. But if there's an abundance of renewable energy, an overgeneration, what we can do in those shoulder seasons, the spring and the fall, mostly the spring, we can take that that energy that otherwise would have been curtailed, and take that over generation to create hydrogen and store them in these salt caverns, so that when we do need it in the summer, we can take out those reserves and burn them through the summer when the load is really needed for air conditioning and all the other activities that typically happen in the high load months. So really, the unique part here is that there's an opportunity to do some seasonal shifting of renewable energy through the storage of fuel. And just for the sake of scale, I have a visual here on the right that talks about the size and the scale of these caverns that we're talking about. So one cavern itself, it would be large enough to hold the Empire State Building. So we're not talking about small things here. We're talking about a large amount of fuel that we would be able to hold. And again, for context, a typical cavern would be about 4 million barrels, which equates to more than 5,000 tons of hydrogen, which is equivalent to 200,000 hydrogen buses, 1 million fuel cell cars, and 1,400 tube trailers. And then that would be the equivalency of one cavern at the site. Because of the large scale that we have, and that those formations are quite large, we have the potential to build hundreds of these caverns on the IPP site and the adjacent property. So putting it all together, we have the renewables, potential for renewables because of where the Intermountain Power Project sits, to take those renewable energies that are coming from Wyoming, Utah, Nevada, California, use the transmission systems that we have to get it to create fuel through electrolysis, through electrolyzers, changing the abundance of water that we do have, changing that water through electrolysis into hydrogen gas. And then at that point, we would have the two different options. We could, if it's not needed, we could store the hydrogen fuel in the underground salt caverns, which would allow for this seasonal shifting. Or if it is needed, we take that fuel and we burn it through the combustion turbines at the IPP site. And so it's an amazing opportunity to utilize different existing technologies, put them all together into this unique way of generating and storing electricity. So, one of the real benefits of this, of course, is as we transition from coal to natural gas, and then to a fuel mixture of hydrogen and natural gas. Really, the goal here is to create is to eliminate a lot of these emissions. You'll see from this chart. I know that there is a lot going on here, so let me just kind of break it down here. On the y-axis, we have the amount of millions of tons per year of CO2 emissions coming from the Intermountain Power Project. On the x-axis, that is time. If we look at the solid red line on the left, that is historically the emissions profile of the current project, the coal project. As we projected out that dotted red line, we'll see as we begin to shut down the coal plants, as the capacity factor on the coal plants begins to reduce because of the additional penetration of renewable energies, we're going to start seeing a decrease in the capacity factor of the coal units, with an eventual drop in 2025 when the coal units are retired and the natural gas units go online. You'll see here in that dotted blue line, as we go across the y-axis or the x-axis, that is the projected profile of the natural gas system. Right below that is the projected profile of the fuel mixture as we put more and more by volume into the system. This is the savings that we would be getting on the emission side. I've highlighted a couple of breakpoints here. 2025, that's when the coal units retire. We would have an opportunity later on in the new project in 2035, 2040, to do these major overhauls to add more capability, to take higher volumes of hydrogen through when we do those major overhauls. And then, of course, the ultimate goal in 2045 is to get to that 100% clean energy, so that we're no longer relying on fossil fuels. Again, we'll have the storage, will have the capability of utilizing 100% green hydrogen with the modifications to the new natural gas unit, and to get to that that goalpost of 100% clean energy by 2045. And so, you know, that this is again a unique project, and its uniqueness comes from the ability to take those existing technologies, marry them together into one project, and really the hope is to drive the industry and the associated infrastructure to be able to accept something like this. And I think as we look through so far what we've been able to do, we've been able to see that it's very possible to do, and it's going to take a lot of work, of course, but you know, we're committed to getting that done. So with that, thank you all for, again, the opportunity to highlight this project. I think it's going to be amazing. We have worked with a lot of people in the industry, and I think you know, the partnership with the regulatory agencies and just getting the word out there that something like this is possible, I think is a major step. So thank you for the time, and I appreciate the opportunity.
Well, thank you very much, Greg. I certainly look forward to observing the progress of this project over time. Our last presenter today in the infrastructure panel is Jack Brower. And Jack's going to talk about hydrogen infrastructure. So please go ahead and begin when you're ready.
Thank you very much. You can see my screen, correct?
Yes, we can. Thanks.
Yes.
Thank you very much. I appreciate the confirmation. All right. So do we really need hydrogen and hydrogen infrastructure? I know you already had some people talking to you previously about hydrogen itself, and so I'm going to not spend too much time on that, although I would like you to recognize that hydrogen is the perfect complement to batteries, solar, and wind. And there are 11 specific features that we have highlighted in this review article that you can review for yourself, because I think hydrogen is the essential piece that we are missing in the state of California for achieving 100% zero carbon and 100% zero air quality emissions. I encourage you to look up this review article. We have more than 300 references documenting all of these 11 features. And I'm not the only one that's saying this. There are many people saying this. I was fortunate to work with a whole bunch of scientists from around the world to publish this paper in Science a couple years ago, and it identified the key role that renewable energy carriers and chemicals that are required to achieve zero emissions. And from my perspective, hydrogen was the most important and ubiquitous of this, as indicated in this diagram that appears in that Science article. And I suggest to you that one of the most cost-effective ways in which we can achieve our zero emissions future is to transform our current natural gas infrastructure into one that eventually is delivering only renewable hydrogen. We published a paper in Progress in Energy and Combustion Science on this very topic. And if we consider both greenhouse gas and air quality emissions, this transformation of the gas infrastructure is essential for us to meet our policy goals. And again, I encourage you to look at this review article, more than 200 references. We document this very, very carefully. This is what we need in order to meet our zero emissions policy goals. And we've known this for a long time, not only here, but also in various other jurisdictions like Germany and Japan and Australia and many other countries. We in the early 2000s were simulating Texas wind farms because they were being curtailed and they were causing grid outages. And we showed that you can actually take excess wind power when it's available, as shown in the green here, put it into electrolyzers and store that into adjacent salt caverns. Texas has 3,500 salt caverns, okay? And we can power an adjacent community, not only through daily changes, okay, in the availability of wind power, but also in seasonal variations. And you can see here that the pressure and temperature dynamics of the salt cavern are fine. They're held within the maximum pressure and temperature limits, but they also take wind power that's available in excess in January, February, March, and in April. and they deliver it back to that community in July, August, September. This kind of hour by hour and seasonal shifting is possible with hydrogen energy storage. But what if we don't have a salt cavern? And that's what gets me to what I think we must do here in the state of California. We do have a tremendous resource in the natural gas system, which even if we tried to shut down, as was indicated by the PUC publication or presentation, we would need a lot of this infrastructure to remain in place in order for us to introduce all of the solar and wind we want to introduce. So let me suggest an alternative. Let us use this vast transmission, distribution, and storage system instead to store renewable hydrogen. It has the equivalent of 13 terawatt hours of electricity storage, even including the low round trip efficiency. This is worth $2.6 trillion in DOE future battery costs. This is extremely valuable resource for us. Even if we stored hydrogen only at 5%, okay, that would be worth $130 billion if we had to install a battery of that size, 650 gigawatt hours. So those numbers are so big, I have to compare it to something I know. So what about UC Irvine tuition? If we paid for the entire population of Orange County to go to UCI, it would only cost us $39 billion. Not as valuable as this resource. How about if we paid all the tuition for all University of California schools, okay, and gave them free tuition in perpetuity? We could do that for just the interest earned off of this battery, this energy storage system. So I want you to think about this, okay? I want you to know how massive this system is and how massive a contribution it could make. If we simply put solar in this 20 miles by 20 miles square area here, and we closed the valves that I'm showing here, okay? If we did this and put that renewable hydrogen into the gas system, of course, we'd have to do some research. I'm going to talk about that a little bit later. How much of a contribution to the renewable future do you think this could make? Just this one project. This one project, 20 by 20 miles of solar in the desert, and just using the gas system to store it and transmit and distribute it, contributes 40% to California renewable energy. Okay, you have to realize that the current gas system is a massive energy resource. So I'm not the only one that's saying this. A lot of other jurisdictions are. You heard from Janice Lynn earlier. This is a slide from her organization, the Green Hydrogen Coalition. But the key thing I want to point out is they're already approved to inject 3% hydrogen into this pipeline in Canada. How about the Netherlands? In the Netherlands, they're already injecting up to 12% hydrogen in that natural gas infrastructure. How about this project? Also, again, from Janice Lynn. Okay, ships for international trading and shipping of hydrogen are already part of the evolving hydrogen infrastructure that Australia and Japan are deploying. And finally, I just want to note, there are huge investments in hydrogen specifically that are going on in Europe. This is just one example. This is the German plan to invest 9 billion euros in hydrogen. Okay, 9 billion in Europe and 2 billion elsewhere. Maybe we can tap into some of that. So what are the infrastructure issues if we are to transform this gas network and storage facilities into renewable hydrogen? I want to suggest that the first one is economics, because this is an example of a study we did in northwestern US. So this is Oregon and Washington and some parts of Idaho. And this is just showing the hourly demand dynamics for a whole year of gas and electricity. And the gas peak in any given hour, okay, is 70 gigawatt hours. This occurs around December 19th, okay? The electricity demand is about 30 gigawatt hours. So let's assume that we get rid of the gas system altogether and we just have to deliver that through via electricity. What happens is the combined peak is 95 gigawatt hours, almost the additive power capability of the gas and electric grids put together. This to me suggests it's not a viable thing to get rid of the gas system altogether. If we wanted to fully electrify just these demands, just gas and electric demands, not even counting transportation, we must triple the power capacity of the electric grid. That's not going to be as economic as transforming both. The second issue is hydrogen safety. Now, hydrogen is a fuel, just like other fuels, just like natural gas is, okay? And as a result, it has flammability challenges, it has tank pressure challenges, it has mechanical damage challenges, it has leak challenges. When these sorts of things occur, yes, hydrogen has a risk. I want to suggest, however, that most people have not thoroughly explained how hydrogen can be handled safely. I have a whole 1.5-hour lecture that I can provide on this topic, but let me just suggest that there are many characteristics of hydrogen. It not only has the broadest flammability limits, but it also has low ignition energy at stoichiometric conditions, the highest diffusivity and lowest density of any fuel we know. When you put these characteristics together, in the event of a leak or accident situation, hydrogen can be safer than the current infrastructure fuels that we use. Now, we must know that it's different. When we know it's different, we can safely move it around in society. But it's not familiar, so there are a lot of things that need to be done. Okay, so there are things that need to be done. And recently, I suggest there's been a lot of disinformation. As a matter of fact, there was a Forbes article that had this very picture of the Hindenburg on it saying that hydrogen's not safe. And as a matter of fact, if you look at the Hindenburg incident, you'll find out that hydrogen actually saved lives. And it wasn't caused by hydrogen. So what's the third issue for infrastructure transformation? I suggest it might be hydrogen injection into the system and possible leakage from the existing natural gas system. Several years ago, I asked a graduate student to start testing this in our laboratory, and these are some results from those tests. When she came back to me with these results, I said she must have done something wrong, because everyone knows that hydrogen leaks faster than methane. And so I sent her back into the laboratory many times. That's why you see these big error bars on these results here. And she kept coming back to me saying, you know what, I keep trying to find hydrogen leaking faster, but I can't. It seems like it leaks at the same rate as natural gas and 10% hydrogen mixed with natural gas. So we investigated it for a very long time. And we also investigated mitigation measures. So we used a very cheap mitigation measure, just applying a copper epoxy inside of the pipe, okay? And it stopped all the leaks altogether. And then we started investigating, why is this happening? Everyone knows hydrogen leaks faster, right? If it leaks by diffusion, it's three times faster. If it's by laminar, it's 1.29 times faster. Turbulent, it's 2.83 times faster. So the seminal publication of 1992, that's always referred to by Swain and Swain, it shows that it must leak faster. But if you look carefully at this very seminal publication, it presents three different leak scenarios: leak 1, leak 7, leak 2. That also show the same thing that my graduate student found. Hydrogen, methane, and propane all leak at the same rate under some leak circumstances. Now, I can't go into all the details here, but we published the paper just recently, 2020. Hydrogen leaks at the same rate as natural gas and typical low pressure gas infrastructure. This may or may not be a significant issue in other circumstances, but it's an issue that I think can be addressed. What's the fourth issue? Hydrogen interacts with metals differently than other gases. We started studying this using actual SoCal gas pipeline metallurgy and actual SoCal gas pipeline pressure dynamics. And we studied the difference between pure hydrogen being injected into that system and what would happen to the fatigue crack growth rate enhancement that we know occurs, okay? And we did this with, top-rated scientists from University of Illinois, Urbana-Champaign. And what it shows is that there is indeed an effect that hydrogen has, leading to pipeline failure that occurs earlier than it would in this current case compared to air, in other cases compared to natural gas. But let me suggest, it shows that if you start in this year with a crack that is 53% through the wall already, and you operate it under current circumstances with 100% hydrogen in it, it still will take 80 years to fail. 80 years to fail. This doesn't answer all the questions with regard to embrittlement, but it suggests in these early results that with further investigation of other components, other pipeline materials, and where these exist and such, that I don't think this will be a showstopper for transforming our natural gas system into a renewable hydrogen delivery system. So the last point is related directly to what Greg Hune just presented to you. I think that one of the most important things is massive and seasonal storage that renewable hydrogen will enable. And it's already widely used and proven in the types of facilities that Greg talked about, these salt caverns, okay? It's been going on already since 2016. Air Liquide, Praxair operating hydrogen salt caverns in Texas. And here it is, I'm referring to this LADWP project here where they're looking at a salt cavern for hydrogen storage in Utah. And this will provide massive seasonal storage of renewable energy that can be dispatched then through these power plants like Greg talked about. But currently in California, we don't have these types of resources. What do we have instead? We have things that you are familiar with as depleted oil and gas fields. These have not yet been proven capable for hydrogen use. And I suggest there are several research and development needs, but I suggest also it will, if we can overcome these kinds of challenges, like whether or not hydrogen will leak, whether it will react with the petroleum remnants, whether it will react with biological material down there, whether it will store at sufficient capacity, whether it'll be safe. Okay, these need to be investigated. But I suggest to you that this will be one of the most important investments for achieving the 100% zero emissions goals we have and enabling us to adopt all that solar and wind for the grid, but then also decarbonizing other sectors, like these difficult to electrify sectors of shipping, long-haul trucks, and the like. Thank you for your attention.
Thank you very much, Jack. Appreciate your insights there. All right, now we are going to move on to the question and answer part of the panel. I'll begin with some questions that I have for the panelists, and then we'll follow up with questions from the public. So I have a number of questions, and I would appreciate, I might direct a question to an individual, but we're interested in all of your perspectives. So please feel free to chime in on any of the questions. I guess I'll start with James McGarry. Your work at the PUC is focused on planning the electricity sector infrastructure, while Gene focuses on the natural gas infrastructure. So Gene talked about some of the electricity infrastructure investments in terms of new renewable generation capacity and in terms of transmission that we might need. What are some other electricity infrastructure investments that might be considered to reduce the dependence on fossil natural gas?
Hi, can you hear me?
Yes.
Great. Yeah, so thank you, Maureen, for that question. Yeah, as Gene's presentation, I think pointed out, building new generation and transmission infrastructure to meet new demand while simultaneously trying to decarbonize the electric sector is going to be a big part of the challenge of transitioning to carbon neutrality. But the details on how we do that are equally important from a planning perspective. So, for example, when does that new demand show up on the system, and what is the production profile of our generation fleet? So one area to consider for infrastructure investments is that as electrification increases electric demand, it's going to alter the shape of that electric demand. So when people are charging their cars when they get home from work, that's going to exacerbate system peaks, which drives our overall capacity needs up. And as Gene mentioned, electric heating is going to increase electric demand in the winter, which is a time when solar and wind output is generally lower compared with the rest of the year. So to the extent that we can invest in technologies that make those new loads more flexible, i.e. responsive to system needs to the extent possible, then that's just going to make it a lot easier to integrate those new loads with our renewable resources. So for example, to the extent that we can shift EV charging around across the day so that we're reducing stress on the system and taking more advantage of solar oversupply, that's just going to help us reduce our peak demand and also lower our reliance on natural gas capacity. another area I'll point out that we need to pay close attention to is the value of resource diversity in our planning efforts, particularly around long lead time resources and those that offer firm power attributes. So as Jean noted in her presentation, our biggest dependency on natural gas and electric sector that we can predict right now is during those, they might be during those Dunkelflaute periods in a high renewables future where we face prolonged periods of low wind and solar output. So as we think about transitioning away from fossil gas, we really need to be thinking seriously about the types of resources that can help us meet our reliability standards during those Dunkelflaute periods. So I don't know exactly what that looks like. It's probably a mixed bag of diverse resource types, including things like offshore wind, out-of-state wind, long duration storage like pumped hydro and green hydrogen, biomethane, geothermal, and other resources that have those firm attributes. But overall, in answer to the question, I think the clear message is that we are going to need a lot more generation and transmission infrastructure, but there's also probably some really smart demand side and supply side investments that we could be making around making that load integration more flexible and getting more resource diversity so we can decarbonize faster and more cost effectively.
Thanks, James. Anyone else want to add something? All right. I think, Melanie, you began to touch on this, but achieving this level of deep decarbonization is going to require substantial investments from both the public and the private sectors. What are some near-term investments in infrastructure and or the workforce that can put us on this path to carbon neutrality?
I actually think the hydrogen production, whatever infrastructure is required for that, I think that not just California, but the country needs to be looking at that. You heard a lot about hydrogen in everyone's presentations today. There seemed to be a lot of agreement in that regard, and so I would put a marker down for whatever we need to do to up investment in hydrogen and use it to the degree that we can in power generation and in industry. So I think that's one area. I would also strongly advise to invest in CCUS. Again, we saw it in our study of California and deep decarbonization. It was incredibly important for meeting 2030 goals. In the world, it's incredibly important for meeting mid-century goals. And that will require basically a gathering system, a trunk line system, and a disposal system. And so that's significant infrastructure. We're looking at that right now, and the miles of pipe that you would need, et cetera, the retrofitting of plants for carbon capture and sequestration. It's important, but it's also critically important right now because while the Congress has not put a price on carbon or required carbon emissions reductions in some fashion, it has put a value on carbon. And the value on carbon is the 45Q tax credit. That was passed in 2018. The administration, not surprisingly, has not yet issued a final rule on implementation of that, but they've issued partial guidance and says that basically you have to have a shovels in the ground in order to get the tax credit by 2024. And the tax credit is as high as $50 a ton. That's for disposal in the saline aquifers that you have there, but a lesser a lesser credit for enhanced oil recovery. And so getting very serious about that infrastructure and providing some certainty for investors, I think, is another major area where infrastructure investments are needed. I would say one other, going back to hydrogen, we've discussed internally at EFI, we think that we made a big mistake in the early 2000s focusing only on fuels. And I actually did on transportation, I mean, and I did a slide presentation, a presidential lecture at BU, where I just chose headlines, and it was hydrogen, 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 and then it was hydrogen highway goes bust, because California was going to build a hydrogen highway at that point. Hydrogen can be the green gas. It's a fuel. Our conclusion of our California deep decarbonization study was that for the foreseeable future, you're going to need fuel in power generation. For example, that's the 90 days with no wind. We don't see breakthrough technologies for battery storage for some time to come. Pump hydro is great, but it's geographically limited. And so we think for the foreseeable future, you're going to need fuel, and that fuel is hydrogen. Hydrogen has the varied uses, end uses, and in electricity that natural gas has, which is why we look at it as green hydrogen. But it's got issues. It emits it when you produce it with gas. It emits carbon. And so industrial capture is important right now, and get the cost of electrolysis way down. So.
Thank you. Does anyone else?
So this is Jack Brower. May I make a couple comments?
Please.
I want to go back to the previous question too, and confirm together with Gene Spencer and James McGarry of the Public Utilities Commission that one of the most important things for us to do is to install more renewable electricity capacity. And I don't think that we are moving at the pace we need to move. And as a matter of fact, I want to suggest that we probably even need to double the amount that was suggested by the Resolve model, because that only accounts for decarbonizing the electric system. And we need to decarbonize all sectors of the economy using renewable solar and wind. Okay, so but what is needed is a framework in which we can actually have an offtake for that renewable electricity already today and not have it curtailed and such. And I suggest again that I think hydrogen is one of the best things that we could invest in to make sure that that proceeds, because we can start using the hydrogen for some of the storage needs, but also for meeting some of the demands we have in the transportation sector. It's a way to electrify transportation with zero emissions, zero greenhouse gas, and zero criteria pollutant emissions, just like battery electric vehicles. Again, we can use both of these technologies. We need both of these technologies to meet our policy goals.
Okay, thank you for that, Jack. I guess so Jack, I have a question for you about the concept that you provided of hydrogen storage in the existing pipeline infrastructure. And then we've heard several other examples of ways to integrate hydrogen into our energy infrastructure today. I guess, can you say anything about the scale of investment that would be needed in order to make hydrogen a more cost competitive alternative?
Yes, I unfortunately am not the best person to ask that question, because I am not an economist and I haven't looked at the economics of this. So I can only tell you something associated with my engineering intuition. And my suggestion to you is that existing underground pipes and underground right-of-ways, there are probably very low-cost ways of transforming them into hydrogen-ready pipelines and right-of-ways underground. probably without disturbing the ground or any new construction for that matter. And that, to me, sounds like it's going to be way cheaper than trying to introduce additional transmission and distribution electric infrastructure. I think it also will be more environmentally sensitive, not disturbing flora and fauna along the way, and also more acceptable to humans that don't want to see additional power lines put in. It's also less susceptible to PSPS and a whole bunch of other reasons. So I think for resiliency alone, it might be worth it. And I have just an intuition. I don't have any numbers to give you, I'm sorry, with regard to how much it'll cost, but my intuition is it'll be way less than the alternative.
Does anyone else want to comment on the scale of infrastructure investment we might need for hydrogen?
This is Melanie. I haven't looked at the scale of that investment either, but I would say we are also looking at rights of way. Rights of way, I think, have a huge value for a range of infrastructures that we are going to be needing for a clean energy future. And I just can't tell you how valuable I think they are going to be for hydrogen, for CCUS, et cetera, et cetera. So.
Thank you. Greg, based on what you've already learned with the project that you described of transitioning a natural gas, well, a coal plant actually to a hydrogen plant, do you have any insights or observations that might be useful for other industrial facilities that currently rely on natural gas equipment, boilers, and if these facilities are thinking about transitioning to hydrogen? Do you have any insights to share on how an industrial facility might think about that?
Yeah, sure. And I mean, that's a great question. And by no means do I know, how to do that. I mean, as we currently transition, but the things that we have learned so far, I think, are valuable, and I'll kind of answer that in two ways. One, on the higher level, talking just about what we've learned just by framing the project, and then I'll try to maybe go a little deeper into like some of the technical things that we've learned. On the higher level, just like the philosophical things that we've seen, is that we really need to be clear on the vision and what we're trying to do. I think when we start looking at something that's innovative like this, I mean, the thought is that you're going to go leaps and bounds into some new technology. But if you look at what we've done, in general with the different innovations in modern times, it's not a fundamental change in what we do. It's more so a change in how we do it. And so when we look at it through that lens, it doesn't really become as daunting as it may seem. For example, the Intermountain Power Project, we're not really changing what it does. We're taking a fuel, combusting it, and spinning a turbine. The innovation is how we do it. And so the innovation is that, we've never burned hydrogen before, and we've never burned green hydrogen before. And so when we look at it in that sense, it helps to narrow our focus. Okay, well, we're going to still do combustion, but how do we get that fuel to be compatible with, one, the generator, two, the different infrastructure pieces like a salt cavern or electrolyzers. I mean, those things are sort of established technologies, but the thing that is innovative and that is different is that we're going to try to marry those different concepts together. And so when we start to look at how to innovate something, again, it's not so much what we're doing, it's understanding how we're going to get there. And again, that makes the picture a little clearer, because then at that point you can start assembling the right resources, you can start talking to the right people. I mean, the people on this call, are exactly the right people to be talking to and beginning those relationships with. So because they can help you get to how to change things and not necessarily what to change. So on the higher level, I mean, that makes it a little less daunting, because now we understand, okay, we want to get here, but we're not changing what we do. We just need to make sure that when we take the steps to get there, that you know, we have a clear path to do it. And then more so on the technical side, if you're talking about an industrial facility that is looking to transition from a natural gas fuel source to a hydrogen fuel source, the thing that we have come to understand is that fuel supply is going to be extremely important, and it's not as simple as if you want to go 30% by volume that you would just inject 30% into your pipeline and you'd be okay. There's a lot of infrastructure that needs to be put in place locally on the site to make sure that what you're putting in is right. So hydrogen tends to burn it likes to burn, and it likes to burn hot. And so if you're not careful about your fuel mixture, if you don't have the right mixing chambers or calorimeters to verify the amount of fuel that you're injecting into your system, you're going to have a lot of problems. And so it's not as simple as, okay, well, I want 30%, I'm going to crank this dial and push in 30% into my pipeline. It's more so, okay, you have to verify what you're putting in, understand that, you know, if you're getting a fuel supply from out of a pipeline and it's claimed to be at 30%, it could be 34%, but you have to make sure that that's verified before you throw it into your system, because even a couple of percentage points when you're off, you know, it could really start to wreak havoc on your systems. And so I think that's one of the biggest lessons that we've learned so far, is that, okay, we have to be very careful when we start bringing in hydrogen at any percentage that it is verified to be at that level.
Thank you. Okay, I think we will transition to questions from the audience. So again, if you want to ask a question, please use the raise your hand feature, and I will call on you. It looks like we have an R. George. If you would, yes, so thank you, you've unmuted. You can ask your question. Would you please say your name and your organization?
Yes, my name is Ranji George. I'm an ex-employee of SCA QMD, and we actually started the ball rolling on both electric vehicles and hydrogen, and I was pretty much involved in that. The ZEV mandate, even though it was ARB's name all over it, it was because AQMD put considerable pressure based on the research some of us done. So I'm going, the question is directed to James McGarry, the PUC. Hearing all the discussions, and I'm so glad, as one of the previous speakers said, that you're looking at energy storage. Is a very good idea, but seems to be very biased towards batteries. Why isn't hydrogen not going up the flagpole? It's somewhere that, and most of the PUC and seems to be focusing on batteries alone. And as Jack pointed out, and thank you, hello Jack, and it's an excellent storage system. And when will PUC be awakened about the great advantage of hydrogen storage?
Yeah, hi. So thank you for that question. That's a really good one, and I think it's definitely something that increasingly we need to be more focused on. You know, with SB 100 in place, and as we start looking towards our, and you know, with the carbon neutrality goal in place, as we look at deeper decarbonization, then longer and longer duration storage is going to be increasingly valuable to the grid. So, you know, I think maybe one reason why we have been, you know, so focused on battery storage is with what we're asking batteries to do on the grid today is a lot different than maybe what we might need with longer duration storage. So, you know, if all we're solving for is, you know, the intraday ramp and dealing with duct curve concerns, then we can probably do that by stacking a bunch of batteries together. As we start to look at, you know, seasonal storage needs and the type of issues that you just run into when you have higher and higher renewable penetration on the grid, then that's where solutions like hydrogen and other resource types might start to be more and more valuable. Part of it is also, I think, our tools that we're actually using. So on the IRP, for example, we tend to use modeling tools that optimize resource selection on a intraday period over 24 hours, where with seasonal storage, you're going to start to see that value in increments over 24 hours. So it's a little bit of a shift, I think, that we might need in order to start being able to quantify the value of longer duration storage resources.
If I may, can I make a couple comments? This is Jack Brower.
Sure, yes.
Okay. Thank you, James, and thank you also for leading into one of the points I wanted to make with regard to the simulations that are made by the Resolve model, which is actually a very outstanding cost optimization model. But you pointed out that it is a daily simulator, and it simulates 37 typical days with various weights to get the annual optimization that is desired. And so it's not a model that actually has the physical capability of monitoring state of charge of the resources throughout the year. Because of these details, it doesn't really have an ability to simulate seasonal storage and some of these features that hydrogen might better engender than battery energy storage systems might engender. I want to suggest also that what the model is simulating is not necessarily lithium-ion batteries. It's simulating a storage with a capability like that of lithium-ion. If hydrogen could offer that same storage for a similar price, right? A different number, certain number of kilowatt hours, certain number of kilowatts. That's what you are saying the model needs, okay? It is, I know that the features are like those of lithium-ion batteries today, but hydrogen can provide some of those same types of features, certain numbers of kilowatts and certain numbers of kilowatt hours.
This is Melanie. Can I say something on that too? I'm looking for the number. I couldn't find the slide, but we looked at the differences between wind and solar in the summer and the winter in California. Obviously, it peaks in the summer there, troughs in the winter, and it is in terawatt hours, I believe, and a huge difference. And looking at hydrogen for storage, I think is a must do. You need something other than batteries, and the numbers that you hear, wind and solar are cheaper than gas or anything else right now, don't include the cost of storage. And as I said, the cost of the storage is basically limited to 4 hours. And when you look at the cost of storage and you add that to solar, you're getting like $120. And where gas with CCUS is 75, that's the IEA number or EIA number, and so cost of storage will get very high, and especially if you have to meet 11 days in a row with no wind, because it's linear. You just have to buy that much more storage. It's 4 hours, and so I think looking at hydrogen and that for that purpose is essential.
Thank you. We'll move on to another questioner, Amy Mignella. I apologize if I mispronounce your name.
That's correct. Thank you. Can you hear me?
Yes, I can.
Okay, that's awesome. Thank you so much. Yes, I have a question, and I got interrupted several times, so I apologize if this was covered, but perhaps it was only mentioned minimally, because I thought I tracked the green hydrogen presentations themselves in their entirety, but I just wanted to understand what the current estimates are with respect to the water requirements for this technology generally, and then as it's being depicted here in terms of scale, especially from the Irvine professor, Dr. Brower, just because obviously some of these regions, especially the map that you were showing, Professor, is in a very water constrained part of the country versus Europe, which most of those sites do not have the same water constraints. Not that they don't have to care about resource impacts, but I'm just curious if anybody can respond to that. Thank you.
This is a very good question. This is Jack Brower from UC Irvine, and I thank you for that question. It is an important question. And water resources are a scarce resource here in California, and they're especially scarce in that 20 by 20 square miles of desert that I showed on the map. So I want you to know that we have done very thorough analyses of that, and in every single case when we analyze it, we find that the amount of water required for producing the hydrogen from the renewable electricity is a very small amount in comparison to the water we already move around in society. And let me give you a couple of anecdotes. We could power the entire light and medium duty fleet in Southern California. Okay, so make every single one of these light and medium duty vehicles a hydrogen powered vehicle and annually produce all of the hydrogen via electrolysis using less than 1% of the water coming to Southern California in the California aqueduct. Okay, so this is just one touch point. Okay, now 1% of that water is a lot of water, but in comparison to what we already move around in society, it's a small number. Another touch point, every single household could be made a completely hydrogen powered household with just one toilet flush of water per day, just 1.6 gallons, okay? And so if you start thinking about these kinds of things, we also did the analysis, for example, for totally decarbonizing the entire LA Long Beach port infrastructure. That includes all the trains, trucks, ships, everything that's in the entire port. How much water would we use? And it's less than 1%, it's less than 0.1% of the water we use in the state of California. Now, most of it is used for agriculture, and it's like, okay, it's not available necessarily where we want it, okay? But I want to make one last point with regard to this, okay? Yes, I consume some water in that desert location when I make the hydrogen, and then I deliver it in the pipeline to a resource that is in Burbank, and that resource in Burbank converts it back to electricity. When it does that, though, it returns the water to the earth. Now, that water's in a different location, but the earth has a 1-year cycle, about, whereby it will return it again to its original location. So it is something that the earth allows us to do in perpetuity that is sustainable. It's a self-renewing cycle of water use.
Yeah, I could, this is Melanie, I have just pulled up a slide just for information, and you're very right to question water use. And again, I'm in New Mexico where water scarcity is a huge issue, and just pulled up a figure. Wind and solar PV use very little water. Okay, I'm just CSP, concentrated solar, both water consumption is not returned to the earth. Water consumption and water withdrawal, a CSP is very high. It's surpassed only by nuclear. Nuclear uses both, consumes and withdraws a lot of water. Gas combined cycles are pretty low, and although more than wind and solar, and coal plants use a lot of water as well. So that's just to give you a relative sense. I can't tell what the units are on my slide, but water is a huge issue that we need to pay a lot of attention to, particularly in water scarce areas. So.
Let me make one additional point, please, directly related to this. The current infrastructure that we use uses way more water than is required for the hydrogen infrastructure. What do I mean by that? The traditional thermal power plants use water for cooling, and the traditional fuel refining operations use all kinds of water. I suggest we're going to use less water making renewable hydrogen.
I think to piggyback on that, Jack, you know, when we ran some calculations on the Intermountain Power Project and the water needs to get to at least that first goalpost of 30% hydrogen by volume, we're looking at 194 acre feet per year. This is the ultra pure demineralized water. If you take it back a step, if you just took the raw water and then processed it, the part of that's going to be, you know, not going to be part of that 194. But as we look at it just completely with the water input, we're looking at 243 acre feet per year. And just to kind of give you the scale of what we have and what we historically had on the project, we have 5,600 acre feet per year. So I mean, really is to emphasize the point, it's really not a ton of water relative to what we have been, what we have.
Okay, thank you. I'll ask another person for their question. Sean Ebnet. Sean Ebnet, are you still here? You are muted. By yourself. Yes, okay.
Thank you. Well, first of all, great presentations, and really quite enjoying this forum today. I represent Ørsted. We are a integrated utility in Europe, but worldwide we are a renewable power developer. And so in our view, hydrogen has a really key role to play. For our part, we are developing working on the scale up of electrolyzer technology in the UK. And we have recently announced our involvement in the targeted 1.3 gigawatt hydrogen hub to fuel airline, maritime shipping, and road transportation industries in Copenhagen by 2030. So in our view, hydrogen and renewable power is one and the same. We think hydrogen is just a more appropriate energy carrier in certain applications, including the hard to decarbonize sectors like transportation, agriculture, and buildings. We also think hydrogen can help California's solar and wind resources reach new applications and sectors that wouldn't be reached otherwise. So as the state increases its use of solar and wind power, it can pit otherwise curtailed power or dedicated off-grid renewable power to generate hydrogen for storage and later use, more effectively storing molecules than electrons. And in many of these applications, you know, we see that there's a lot of the fundamentals exist in the California market that we are seeing in Europe. And there's been some quite scalable announcements made in Germany, announcements made in Saudi Arabia and other parts of Europe. And those key fundamentals exist in California. So, of course, the key is to get to scale. We get to scale, we get to cost effectiveness. So we get to cost effectiveness, we get the deeper decarbonization and air quality improvement. And the sooner we get to one, we get to the other. My comment is really more towards the policy side of California, because the trigger for all of this is policy. California can replicate the success achieved through the renewable portfolio standard, and we would like to see a similar policy targeting renewable gas standard. And so our view is the state, for its part, should not be passive and wait for scale to happen and costs to come down. It should facilitate this, because we'll see the same effectiveness we saw in cost reductions of wind and solar that we see today because of the RPS. And that's how we believe the RGS will drive the cost, and the scale exists already, and we're starting to see it. So anyway, more of a comment than a question, but for those involved in shaping the policy of the state of California, please look to your own successes on the RPS and recognize the scale that's being achieved in other markets. California has all the fundamentals in place, and as an investor and a potential developer in this market, we would love nothing better to replicate what we're doing in other markets in the state of California. So thank you for this seminar and for the opportunity to make a comment on this. Thank you.
Thank you, Sean. And I would just remind everyone that you may submit written comments at the link on our carbon neutrality workshops and meetings webpage.
Hi, this is Jean. I actually kind of wanted to respond to that last comment.
Please do.
If that's all right. Okay. So I just wanted to point out a difference on the gas side that I think it's important for people to understand. And that is, we at the CPUC at least do not have jurisdiction over the procurement of gas by what we call non-core customers. So large industrial customers, electric generators, we do not control their procurement. So it's not completely straightforward to emulate RPS. That is a deregulated market, and they procure their fuel themselves. The only procurement we control, or the vast majority of the procurement that we can direct, is for core customers, which are residential customers. And you know, as I think CARB's goals are to electrify residential customers and focus renewable gas on large industrial customers, and that's precisely the customers that we do not, that we can't do anything about their procurement. So I just wanted to make sure people understood that.
Thank you. Okay, the next question is from Cedric Twite. And Cedric, you're self-muted. Yes, okay.
Cedric, can you hear me?
Yes.
This is Cedric Twite from Sierra Pacific Industries. My question is, in the context of forest, and considering the unprecedented wildfire threats that California is facing due to overstocked forests, and because treatment of these forests is necessary to prevent them from releasing the carbon stored in those forests, and protect the valuable watersheds they are growing on, why is biomass not being leveraged more aggressively as a strategy for supplying a larger percentage of baseload power, since it could support wind and solar and also provide a cleaner means to dispose of this material? And I suppose the CPUC representative could answer that, since you all, the others, are all very focused on hydrogen and electrolysis and what have you.
I don't know much about biomass, to be perfectly honest, but I can take a quick stab at it. And James, if you want to add something, I think from the PUC's perspective, we always have to be really conscious of costs. Rates are high in California, and we need to be careful about increasing what ratepayers are already paying, particularly now. I believe a third of California ratepayers are currently on CARB, and after COVID-19, which is the program to help low-income people pay their electric bills. And again, I'm no expert on biomass, so I don't want to overstep my expertise, but my understanding is that it is quite expensive. So James, if you want to add anything.
Yeah, sure. I can jump in. Yeah, I'll know. Before I worked on IRP, I worked on the RPS team at the CPUC and worked on some bioenergy issues. To the extent that biomass can be leveraged as a wildfire reduction strategy, we do have programs at the CPUC that address that. So there is a fleet of biomass power in the state of California. We have the BioRAM program, which is directed at keeping some of those plants going through contracts with the utilities if they utilize a certain amount of high hazard fuel. We also have targeted procurement programs for small bioenergy resources through the BioMat program. But as Jean noted, that they are the contracts for these facilities are significantly above market. For new facilities, for new small biomass facilities, PPAs are about $200 per megawatt hour. So I would say that we are doing some targeted programs on bioenergy in terms of overall optimization in reaching our other goals, we consider bioenergy resources, but because of the high cost, they haven't thus far been selected. But we will continue to include bioenergy as eligible candidate resource when we are looking at procurement.
Okay, thank you. The next question is from Ken Dragoon.
Hi, thank you. Yes, from Renewable Hydrogen Alliance. I had a question for Dr. Brower. Given your findings on leakage and embrittlement, I think I remember reading that sort of the upper limit on hydrogen and gas pipelines was about 30% due to the end-use appliances needing change out after that, but utilities are quoting much lower numbers, and I believe these are all by volume, so it's even lower by energy. So given your findings, why do you think the utilities are just being really cautious, or are there other issues that they're running into that we didn't know about?
Thanks for your question, Ken. Nice to hear from you. Yes, you're correct that I'd say more scientists think that it's around 20%. And it is most of the time due to end-use appliances, and not during steady state operation, but during the light up and startup phases when you have let's say an electric or a pilot light that's going to ignite the mixture. So it's yes, those end uses have constrained limits to about 20% or 30% by volume. Let me suggest that would be a huge and great contribution to installing more and more wind and solar throughout the state. If we could take a bit of it and put it into the gas grid, partially decarbonizing the gas grid, it would enable us to dramatically upscale our wind and solar investments. So even those kinds of small transitions on the gas side might have a huge benefit to the electric side. But finally, I suggest that's not the end game. The end game is we must remove all of the fossil. And so there has to be some kind of piecewise transition of pieces of the system to 100% hydrogen. And that's when it calls for, yes, the swapping out of appliances or retrofitting appliances. So if you take a gas stove and you want to convert it to a hydrogen stove, you know what you have to do? You have to introduce to the burner only a different hole size, okay, for hydrogen. So again, my intuition suggests that that's going to be a very cheap retrofit. I can take my gas range and I can convert it from a natural gas range today, just like you do when you buy a barbecue. If it's for propane, you just drill a different size hole for natural gas. Okay, it's going to be the same for hydrogen. So that my suggestion. It's not just mine. The UK people have decided it's going to be a lot cheaper to transform appliances from natural gas to hydrogen than it is from natural gas to electricity. Anyways.
Okay, thank you. The next question from Kevin Medeiros. Kevin, are you there? Kevin? Okay, I don't think he's got a question. How about H.E. Chris Peoples? Let's see. Let's see, sorry. Chris, there, yes, I think. Now can you
Thank you, and thank you for an excellent presentation. I just wanted to make a couple of comments that address both Ms. Jones's issues and some other issues that have been brought up. I'm a member of the board of directors of the Alameda Contra Costa Transit District. We've had a hydrogen bus program for almost 20 years, and we've trained all of our operators and all of our mechanics in basic hydrogen safety, and all of the mechanics in basic troubleshooting, very basic troubleshooting. We're in the process of training up mechanics as they come up for training in much more advanced troubleshooting and in repairs. And that's all being done with our existing ATU, Amalgamated Transit Union personnel making a full diesel salary. And it's been an interesting thing because particularly these guys, and most of them are guys, the older guys, they bleed diesel when you cut them. And so transitioning them to a hybrid battery hydrogen fuel cell is an interesting thing. We've set up a zero emission bus university. Our first outside folks are folks from Urbana-Champaign who are getting 5 of the New Flyer 60-foot hydrogen fuel cells. The other thing, and a number of you talked about this, we serve 13 cities and 9 unincorporated areas in 2 counties. And so we've had to train the first responders on how to deal with hydrogen. And that's been a long and difficult process, but we've done it. And so a lot of the problems that you're talking about are solvable, and we have in fact solved them. So let's go to it.
Thank you. Okay, we're going to do one more question. Unless, did anyone want to respond to the last comment? Okay, we'll have one more question and then we will go to closing remarks from each of the panelists. David Park.
Hi, yeah, this is Dave Park with the California Fuel Cell Partnership, and this has been a great session. Thank you so much. It's great that hydrogen is so well recognized in these conversations, and there's a really great focus on system-wide interactions of grid and energy storage and the hydrogen connection, which is really well appreciated. Noting that we're arguably in the early phase of ZEV adoption, I'd like the panel to address the topic of ZEV fueling infrastructure and the topic of scalability, and the scalability of electrical infrastructure versus the scalability of hydrogen fueling infrastructure.
So thank you for that. This is Jack Brower. Maybe I can take a stab at that one. I think that your question deserves a quite thorough and detailed technical analysis to answer it properly. But there are several anecdotes that suggest, and some international studies in other jurisdictions, that show hydrogen infrastructure costs more when you have small amounts of small amounts of vehicles that you are transforming, but it costs a lot less when you have larger amounts that you are transforming. And we see this also with some recent investments of bus fleets, for example, right? So bus fleets, if they want to electrify 10 buses, it's better to go with battery electric. But if you want to do 100, it starts to become difficult to charge all 100 buses at night, and the infrastructure cost for installing all of those chargers is more than one fueling station for 90 buses, 90 hydrogen buses, and 10 electric buses. You know, so there's evidence that shows that as you go to higher and higher proportion of electrification, okay, that hydrogen might be a better vector for electrifying and be cheaper for electrifying the last 70%, the last 50%, the last 30%. Let me make one more comparison. In my neighborhood, we have about 30% of our neighbors that are driving battery electric vehicles, and we're all charging them at night. And our infrastructure is brand new. The neighborhood's only 15 to 20 years old. But if every single one of us got a battery electric vehicle, we would have to invest in a new transformer and some new wires and some new electric infrastructure to make that happen. That might be more costly than investing in one hydrogen fueling station to make all the rest of the vehicles zero emissions using electricity to make renewable hydrogen that gets injected into, let's say, a station that can serve 1,000. Let me mention one last thing. Some awesome companies are advancing this technology very significantly, and in particular, First Element Fuel. You got to check these guys out, okay? Former UCI grads that started this company. They just installed a station that is 1,400 kilograms per day, 4 nozzles. It's the state of the art. It's going to lower costs very substantially for getting renewable energy into our vehicles.
All right, well, thank you for that. Thank you all for joining us today. I guess we'll just go around in the same order that you gave your presentations, and if you'd each just make a few closing comments, we would appreciate that. So Bethany, would you begin, please?
Yeah, I would just say this conversation has been fascinating, and these are the types of solutions that not only will they get us to the economy-wide carbon neutrality goals, but they're also the solutions that will minimize or even eliminate potential job loss as we decarbonize from the fossil fuel industry. And while some new skills will be needed, I think the occupational structure is really similar to today, like a lot of jobs in the skilled trades within apprenticeable occupations. So we have the workforce infrastructure in the state of California to realize some of these ambitious goals and pursue some of these pathways.
Thank you. Jean, do you have some closing remarks?
I guess, it has been an interesting conversation. I think one thing that, for me is a concern is again, back to costs. I think we always need to keep our eye on the costs, because as I said, the ratepayers are pretty heavily burdened. So we need to think about how can we do this in the most cost-effective way possible going forward.
James, do you want to provide any closing thoughts?
Sure, yeah. I guess I'll say that, as a energy planner in the state, we just to meet our current, RPS and GHG goals, we have to build a lot of stuff. We're going to need a lot of infrastructure on the transmission side, on the supply side. Longer term modeling we've done for 80% reduction in GHGs by 2050. We have some modeling on that. It's going to require a whole step change in the amount of infrastructure build out that we're going to need. And once we start looking at carbon neutrality by 2045, it's a step change from that in terms of what we need to do, and probably involves certain technologies that are not widely deployed today. So I think that conversations like this, where we're exploring, innovative technologies that that might be needed for the grid of the future, are extremely important. So I'm glad that we were able to discuss all of this today, and I'll echo one of the earlier commenters who said, let's go out and do it.
All right, thank you, James. Melanie, what are your final closing thoughts? Oh, I think we lost Melanie somehow. Greg, do you have any thoughts you'd like to share?
I would. Thank you for that. So one, of course, thank you for the opportunity to present again. Two, I think, as we go through more of these presentations and these workshops, I am always encouraged just by the level of engagement and just the fact that we are looking at these types of issues holistically. I mean, we're not just talking about things on a technical level, which I think the hurdles there are surmountable, but we're looking at it from an infrastructure perspective. We're looking at it from a cost and economic and jobs perspective, looking at it from the regulatory side. Those are the challenges that we're going to really need to get through. And so I'm of course encouraged, seeing the diversity on this panel, looking at the problem from different lenses makes me really encouraged that we can really get there. So again, thank you for the opportunity. I'm glad to be here.
Thanks. All right, Jack, and you can close it out.
Thank you. Thank you very much. Wow, I really appreciate the opportunity to speak here. I'm really glad to have CARB engaged and involving so many people and diverse opinions and different disciplines that are all going to be required for us to achieve our policy goals. I'm honored to be able to speak to you all. I also have, with all of our talented graduate students and postdoctoral researchers, been investigating the idea of an ultimate sustainable society for a long time. And I know with certainty that we must invest more in our solar and wind. I know with certainty we must invest in battery energy storage technologies. And then you got to look for what else do we need, because we need more than just that to reach our policy goals, especially if we want to decarbonize and make zero criteria pollutant emissions the reality in all of our economy. And I keep coming back to hydrogen being a major part of making that happen. And if we invested, if we just made the policy decision to invest in hydrogen, to say that that's going to be our energy vector, it has multiple benefits that it provides to the electric grid and to a whole bunch of other end uses. And if we invest in it to the scale that, for example, Germany is currently decided to invest in hydrogen, I can almost guarantee you, our economic analyses show that hydrogen will be cheap. And I want to make one last statement, please. I believe the fossil fuel era will not end because of our policy to ban it. It will end when we're able to make renewable hydrogen cheaper.
Okay, well, thank you all very much. We really appreciate the time and energy you put into preparing and sharing your day with us. We've learned a lot, and I just want to remind everybody in the audience that you can submit written comments on our carbon neutrality meetings and workshops webpage. We appreciate everybody's interest in joining us today, and we look forward to continuing this discussion around carbon neutrality with future workshops. So thank you all for joining us, and have a good afternoon.